closer, please. Can you hear me? How is the sound? Brian, how's the sound? Can you hear me? No? No, when I say something. Is the microphone on? The microphone's on. That's all. Then I'll start. What about now? Yes? Okay. Can you hear me? Is the volume on? The microphone is on. Can you people online, can you hear me? Just write in chat. Yes, okay, they hear. It's all good. So, good morning, everyone. This is the day 2 of our Open Data Science Europe workshop. We have a really rich program today. Lots of talks. There will be lots of also live presentations with demos. And we expect a lot of discussion as we had yesterday. We're very happy to have also people following us online. We kick off. Today's theme is largely focused on land cover mapping, forest mapping, biodiversity mapping. So we focus a bit more on land cover mapping today, and then also there will be something about soils. And there will be a demo in the lunch break. There's a demo of the virtual reality, augmented reality of the Open Data Science Europe viewer. A colleague is connecting from Prague to show us that, to give us the demo. We kick off with a keynote by Professor Martin Herold, Professor of Remote Sensing GIS here at Wageningen University, who's also transitioning to a new position in JFZ Potsdam, where he will lead the group on remote sensing. So we're very happy to have Martin Herold with us here, and he's going to do a talk about global land cover mapping and assessments. With this, I just want to pass on the floor to Martin, so just give me a second to pass the microphone. The keynote is 40 minutes, but we will have some time for questions. Thank you, Tom. Thank you for the introduction. Good morning, everyone here in the room. Good morning, everyone online. Nice to be on the stage again. It's my first time in 1.5 years. Nice to talk to people actually in the room, which is really nice. And that's why also thanks to the Open GeoHub team for making it possible. I know it's still difficult to mobilize crowds to come, so it's good to see at least some faces here and also a good community online to follow this. So thanks very much for organizing this event, which I think with this topic we rarely see in Europe. So very happy to be here and very happy also to be given the opportunity to talk about a topic that I've been working on for a number of years. And yeah, a bit of keynote also gives me the opportunity to reflect a bit. And so my idea today is to really go through a couple of things that I think are important, which are evolving, which are happening now in the global land cover monitoring and assessment domain. Working in this field for a number of years now, and if we think about where we were 10 years ago, we will mostly talk about global land cover maps with a couple of classes, 500 meters to 1 kilometer, mostly for the climate modeling community, a lot of one-time, rather inconsistent data sets and so on. And I think we've came quite a long way. And I think that's my big message today. We'll never had such opportunities, such databases, such information to really serve quality land cover data to a wide community of users and applications. And I'm going to go through 5 main things. First of all, a bit of an update on what's happening. Of course, we'll draw a bit on our own research here at Wageningen and with our partners, what's new. Then I'm going to talk about what's next also in terms of higher quality measurements, approaches, uncertainties. Always very important to talk about. Something more generally about accuracy and also looking to users. So about the first point about tracking global land dynamics, I'd like to show a slide that actually Curtis Woodcock put together a few years ago. What you see on the left-hand side is basically the Landsat archive. It's a certain area somewhere in the US, but what you see is basically the whole Landsat archive. You can see on the bottom it started from 85 and it goes all the way to today. You see every image ever acquired, so you see cloudy, cloud-free, all kind of data. And then you see basically on this, the observations continues, you have a land cover map that's formed, that is on the right-hand side, and then you see also a bit of a land cover change map that's also evolving at the same time. The point of this is, the large archives we have, the consistent high-resolution time series basically allows us to characterize land cover more or less at any point in time for any given period, and includes both the assessment of stable land cover conditions and also change dynamics. And so basically, we go in, really assess both characteristics and any changes over time in a systematic way, and basically at a 30-meter resolution in this case also using Landsat data. Now that's conceptually how this has evolved to from these kind of all one-time 500-meter kind of maps. That's the concept that basically we're more or less using. Of course, there can be improvements in terms of data and approaches and how to get there. Of course, particularly when it comes to global land cover change, we're not there where we want to be, but still, conceptually, it's relatively clear. We have seen then, based on these concepts, the evolution of also services to Copernicus Global Land Monitoring Service to produce global land cover, right? Currently at 100-meter resolution. It's annual since 2015. It's 100 meter. It includes both discrete land cover classes and land cover fractional layers. So fractional layers include tree cover, shrub cover, herbaceous cover, agriculture cover. So there's 9 fractional layers. So you have a characterization both in terms of discrete classes and fractions. And what's very important for this operational system, it's basically a combination of a training data collection system. It's basically just acquiring training data in a continuous way. You have basically the map production system where you basically produce a map based on training data. And then you have an independent validation system that's basically continuously collecting reference data to make sure the products can be assessed regularly in terms of their quality and their characteristics, also for different users. That's an operational service. I think the plan is also to migrate that to Sentinel data, 20 meters, and so on. And this is not a research project, right? This is really operational services for users. We have the World Cover effort, which will release next month, 2020 global land cover at 10-meter resolution using a combination of Sentinel-1 and Sentinel-2 data. So this field of moving to what we call the global land cover, very high resolution, 10-meter scale, needs quite some effort this year. Also, the point here is we've got to the point where basically a map for 2020. Okay, good. Can you hear me? Is it better now? Is it better now? Good. So back to the 10-meter global land cover. Basically, we see that basically we can process global 10-meter data for 1 year for 2020, basically in the first half of the following year. So that's basically these things are ready to go for production. And then, of course, if we get more detailed in space and time, and we look and we study land cover dynamics, we also learn new things. For example, one of the things we're learning is that actually global land cover land use change is actually 4 times higher than we previously thought. And that's because we look at more detailed data. If we look more detailed, we see more dynamics. We also know that a lot of land dynamics are at a very detailed space-time scale. And particularly with the observation data, we get to look more gross changes, where you don't see kind of this net change, just areas of, for example, the UN is good reporting, but really we look at gross dynamics. And we can look at basically also these phases of acceleration and deceleration of global land dynamics. This is all basically an answer we can now do with the first observation data. The other important point is really that we use dense time series to also produce any updates in near real time. I think there's also a couple of people working on that. So every time satellite observation or a series of satellite observations becomes available, you can check whether there's a certain change in behavior, so whether there's an anomaly initially that you can say, oh, there's maybe a likely change that you can over time assess whether that's actually a land component that's changed yesterday or not. And there's all kinds of alerting systems and tracking certain unwanted land dynamics systems that are being developed as part Sentinel-1 based, forest change alerting for, I think it's 35 countries now in the tropics. It's basically weekly data based on radar data, so cloud-free capabilities to really track it. This is, for example, a logging activity in the Congo Basin. This is basically tracking things on a relatively detailed space-time scale, and second. Yeah. This. So this is like so let me just double check quickly. Is the voice better now? Is the voice better now? And then also, let me start the presentation. I think my screen should be shared now. Sorry for these technical hiccups. It's a technology-wise a relative complex setup, as you know, in these hybrid systems. So apologies for that. Let's go back to the near real-time updating of landmark data and real-time alerting, which I think is also an important dimension of global assessments that we can now look into. So if we then summarize a little bit on the broadly tracking global land dynamics, we have these long, dense satellite archives and some analytical tools to really allow us to produce these data sets that give us important insights in terms of dynamic anomalies and disturbances. And I think particularly with these near real-time kind of updating, it's also an increasing link to human actions. So we can almost track human actions as they happen with these kind of satellite data. Some of the issues or rules of improvement, it uses relatively simple spectral data. It's mostly empirical. It still remains in a few broad classes, and there's actually a relatively limited physical understanding of what's actually happening. We do see changes happening, and we can characterize them, but we don't have a very detailed physical understanding. And I think those are areas we can improve upon, and that's where also we talk a bit about what higher quality measurements could include. And of course, one of them is more structural information. So, for example, there's options now with, for example, LiDAR and radar-based approaches to get really more structural characterization. This is an example that you see them moving as a data set required for the drone. So that's basically not a satellite-based system, but basically tells you on the ground you get very detailed characterization, also of vegetation structure. We can also use this kind of information to track these things over time, as the multi-temporal structural measurements. And then this, if you have the right satellite information, you can actually then use that to try to scale it up to large areas. We have, for example, the JEDI system running on the space station that's acquiring footprint LiDAR at 25-meter resolution, and it gives us something about height and structure of the vegetation. This is just the data for the first 6 months. It's basically a sample-based system, and you can easily use that, for example, sample-based system provided with Sentinel-1 and 2 data. In this case, to extrapolate things like, for example, vegetation height. The new generation of products that are becoming available also then cover not only providing changes in cover, but also changes in height using these kind of data. Then the other area that I think is very dynamic or will be much more important in the future is the hyperspectral domain. At the moment, we don't really have very suitable hyperspectral missions in space to add really much more spectral information to the analysis we're doing. But that's going to change. So NMAP is a system that's going to launch next year. Can you still hear me? Good. I think the microphone went down a little bit. NMAP is going to be next year, and then also it's the next generation of Copernicus satellites. There's a hyperspectral mission that's planned, and that will allow us really to really scale up the opportunities there, also to the global level into more service content. So I think the structural domain and the increased spectral domain are really areas where we can see a lot of progress, where we can really also address some of the limitations we still have. We're still at 70-75% global accuracy for a lot of these data sets. We're still at broad classes. We still have a hard time characterizing particular heterogeneous landscapes where you have a mix of trees and grasses and all kinds of things. So there we know where some of these things can really help us to do, and eventually can also help us to really get towards more hyperspectral, so let's say a bit more detailed characterization on particular changes. I already mentioned that some of these satellite missions are either already there or on the horizon, and the drone-based or the in-situ sensing kind of capabilities we're also increasingly able to calibrate and validate the data coming from these systems. Let's talk a little bit about advancing approaches. Very little, because I think there's also presentations afterwards. Our time, for example, really go into more these, how AI type approaches, deep learning and these things. There's a big movement, of course, also in the land cover domain to make use of these kind of things to particularly characterize more complex things, such as, for example, land use. There was always this notion, well, in the land cover domain, we can basically do land cover, and it's still, if you look at it, that's the main thing you can do. But land use, there's a lot of interest in land use and land use change, and there we can see really make a big progress, because land use is a much more complex issue. It's not only the spectral information, but also information on context, on time series history, on legacy effects, and so on. And these complex features, I think, are best combined to use for land use mapping. I think there's an example here for tracking land use that follows deforestation topics, for example, where really some of these deep learning models have really helped us make a big step forward. The other thing I already mentioned is fractional mapping, so getting away from discrete classes of forests and so on. We need to go to fractional layers. So there, we do see these new approaches really helping us to narrow down the uncertainties, particularly in these mixed landscapes. So if you have 100% forest or 100% non-forest, we are relatively good, but it's the area in the middle where we really struggle. And I think that's where these approaches can really help us to make a big step forward. So these models help us to really get into some of the more complex issues, and we see them particularly for land cover characterization, but also increasingly for land cover change or land use change. We also know, think about globally, land cover land use change is complex. The same change, might it be an urban expansion or agriculture expansion or a certain degradation of a wetland or so on. The same type of change looks quite different in different parts of the world based on natural conditions, and that complexity we'll have to take into account when doing this. What's very important, of course, when using these approaches is that, if you think about machine learning, is that my worry is not so much with the machine. I think with the machine we have great progress. The tricky thing is really the learning. Do you have enough reference data? And on the global level, you want to do something globally. We're talking about a lot of reference data that actually needed to really run these systems. That's probably one of the biggest bottlenecks we're currently having. And that's why, so what I said before, this Copernicus system, the operational system that invests in training data collection, mapping system, and independent validation system. A lot of reference data as much as processing and analyzing satellite data. I think that's the way forward to address these kind of things and really take advantage also of these new approaches. Let's talk a little bit about uncertainties. I think all reasonably available global land cover data have okay validation with it. We've worked hard as a community to create some standards, CEO's Carvel standards for global land cover validation have been around for a while. So I think it's very important that these independent assessments keep being done, and I think most of the serious efforts, I think, are doing that. It's relatively easy now to produce a global land cover map. You can always do it with an MSc student, go on a cloud-based system and run throw some training data at it and stuff like that. But the question is really, how good is it, and how good is it for a certain user community? So I think that's a general thing, and I see a lot is happening there, and that maps without proper validation are rarely put out. And then, of course, if they are not, then I think we have to really question the robustness. I think methodologically, where the validation is moving at the moment is to look really at multi-temporal validation. So basically, how can we also develop reference data collection system that are also providing regular updates? You have basically a bit of a sample that you use for you have stable land cover characterization. But what if you have new data, a new year coming with new data, you have to collect more reference reference data to also say how good is the map that I'm producing for 2020 versus, for example, 2015. So if you update the reference database, and there are all kinds of sampling issues associated with that. And then if you have multi-date land cover maps, for example, annual land cover maps that you're producing, the issue of stability is quite important. So stability meaning how consistent is the accuracy of the map over time? Are there variabilities? And for example, what we found in the Copernicus Global Land Service, because what you have 2015 was produced first, and that was the first deliverable, and then the following 4 years were done after. And then, of course, there was, because it was a bit of a different effort, to see quite a difference in stability between, for example, 2015 and the follow-up years. And then, of course, limits consistency among the maps, and of course limits the availability or the suitability of these maps. They actually look also for land cover changes. So these multi-temporal validation concepts are evolving, and then of course that needs to lead to also better systems for assessing land cover change, so directly land cover change accuracy. Also, there are some good guidance that is available how to do that. The same example, this is not from the classical land cover domain, but global space-based biomass estimation, where we also see quite some related things. And what is at the bottom is basically a comparison of reference versus map. And you see that broadly for the lower biomass ranges, there's relative consistency in the global pattern of uncertainty. But for the higher ranges, you see quite some variability. So that's where you really see that the maps are rather inconsistent, and any differences or changes to them are likely to be very uncertain. Keeping in mind that also the error sources for this multi-date data might correlate quite a bit, might aid actually a change in estimation, but in general, particularly for biomass maps, for example, they're not there yet. And the same is actually true for the Copernicus Global Land Service. The estimation of change and over change validation of time is in the order of 60%, so 40% commission and 50% commission error using this consistent. So there's still quite an error to use the annual multi-date maps to assess change. It's good. I mean, more than half is correct, but there's still quite some change, which is not correct if you just use the annual maps. It's all in the validation report of the product. So then let's talk a little bit about, then you mentioned already the uncertainties, that it's talk a bit about global advocacy and transparency. It's not only that we use new data and new approaches to produce better data, but we also for purpose. And if you go more detailed, you get more detailed data, you move to 10-meter global land cover, you have longer time series and stuff like that. You also increase the potential users of this data. So the 500 meter or 1 kilometer map was useful for a few people, but let's say 100 meter or 10 map has a much broader user community, and we see it in the download rates of these products in terms of the Copernicus Global Land Service, the land cover products, by far the most popular one. And then, of course, there's all these concepts to do much more user-oriented mapping. The nice thing is, I mean, what the machines we have at hand, you can easily reprocess data. You can, if your user has a certain reference data, some kind of training data, some kind of definition, some kind of cartographic standards that they have, and you can just basically throw it at the data and produce maps user-oriented relatively quickly, at least conceptually. And that's, I think, something we see that's starting to happen, and that's why it's not only one map, but it's basically either a series of maps or targeted processing, depending on what the user needs are. One of the big audience that we have with our data is actually countries, country-level estimation and reporting. For example, for just pick an example of national forest monitoring, reporting to the FAO, but also using data to report for greenhouse gas inventories and all kinds of other, for example, SDGs, sustainable development goals, UNCCD, and all of these things. And we looked at the last forest resource assessment of the FAO, which was just launched recently. We see there is a massive increase in country uptake of also Earth observation data for doing, for example, the forest area and forest area change estimation. So basically everything you see at the bottom left in green, those are all improvements in country capacities, particularly on the tropics, of using Earth observation data between 2005 and 2020. So it's not just the source that we are seeing here, but it's really uptake by countries for their operational reporting service, which is great and shows that actually countries are able to deal with what people might call technology-wise very advanced approaches into their routine operations, also in tropical countries. We then, of course, see that, and that's going a bit beyond land cover, these issues of how can we we have good land cover, land exchange, and how we turn that into greenhouse gas emissions, combine it with biomass stats, with fire data. I think it's Earth observation-driven, more spatially explicit greenhouse gas inventories in forests. I think we see the first generation of those showing up. And I think we see in Europe a strong push towards more spatially explicit greenhouse gas inventories, because they are more policy oriented, they are more action oriented, and it's now a research domain. But I think that's also what I see the next generation of things that will come up and should also be become available for some of the routine use, for example, in Europe and other parts of the world. And then just an example of this is again the Congo Basin. It's combining the alerts that I showed earlier, for example, with the biomass estimates, with a combination of ground and field data. So you not only can get basically changes in forest, but you turn that changes in forest into emissions, so local carbon emissions to certain. On the left-hand side is the selective logging operation. Because you have such detailed data in time, you can almost see a temporal profile of emissions, for example, for a certain logging operation. And on the right-hand side, same area, just next to it is a shifting agriculture system. So that's basically, there you see much more seasonality because it's really related to the dry season and dry season availability. And you can see basically these temporal emission profiles that you can derive in high spatial and temporal detail. And I think that's really, for me, an example of having something that has units, not just land cover, but has units. There's an uncertainty assessment with it. Some uncertainties are still rather high. But this is something that's actionable and it's spatially explicit, and I think that can really support implementation. If you want to, for example, think about certification of logging concessions or tracking illegal activities in forests. So good. Then let me sum up quickly, and then I think if you have any questions, get them ready because this is the last slide. So really, this availability of long archives, time series approaches, big data analytics really has improved land cover characterization. Almost can say it's the golden age. I mean, now at 10 meter, right? The global will have operational data streams. We can expand, of course, in other dimensions, but I mean, it's never been as good as it's now. And then almost to get to the point, what else do you actually need to do a good job for many of the users? I think that we're serving. So it is a golden age. I think from a research perspective, really a much more focus on the structural and the hyperspectral dimension is something that will come up in the years to come, because also the data becoming more available for these kind of things that can certainly further improve our ways, our accuracies, but also our level of detail and our physical understanding on where and why the land surface is changing. We see some of these novel approaches in data science AI to really enhance the characterization really for complex situations, and in particular when it comes to things like land use and so on. The accuracy assessment really needs to include this temporal component much more in the assessment of changes. I think that's still something that we're struggling with. So that's something that needs both development and large area applications. And then, of course, with all that data in hand, I think we're in a much better position to improve our delivery of data towards a broad range of application users and also to actions. I think that's what there's a lot of demand for. Having data reasonably up to date, or what makes the news basically if there are, here it's working with the Brazilian Amazon. If the Brazilian Amazon is burning, basically, the news is made when it's actually happening and not half a year later. Now, so having really data that are reasonably up to date about some of these critical processes really matters if you want to really have an impact. With that, I would like to close my presentation. I think we should have time for questions. Thank you. Let's see. Question: how do we avoid fake news effect and then cover that? Good question. I mean, let's say, we have, or let's say, one of the advantages of satellite data is that everybody who's reasonably skilled can look at an image and kind of see what's happening. So it's not so easy to fake things. I mean, I'm not saying it's not possible, but since we have relatively dense time series data and increasingly detailed, I mean, it's a data stream that is really on the very complicated end to fake. Okay, but there I would say so. Just in terms of what happens in the chain of the land is one thing, and then I think it's very hard when you link it to biomass, for example, or you combine it with some biomass or biomass stock or carbon stock and change data, becomes more tricky because I mean that's at the moment a bit more the uncertain part. Right? It's how much biomass is there and how much biomass is changing. There, I think this is much more tricky, and the best way to go about it is really to have a proper uncertainty analysis. And at least at the moment, these global land programs, they do come with an uncertainty layer. We are, and we have to be honest about it, we still have biases in the high biomass regions coming out of that. We still have RMSEs locally of 50 to 100 tons. And these average a bit out when you go to larger aggregate estimations, but on the local level, those are still uncertainty. Yeah, that's the way we have to report it. I think that's for me the way to go about it. I mean, again, I would say there has been quite some debate. I'm just going back to the Brazilian Amazon example. The data produced, for example, by INPE. So Gilberto Camara was talking yesterday. He was one of the fathers of the INPE road system. They have been up to scrutiny. They have been up to court cases and all of that stuff, and they've survived reasonably well because it was such a clear, defendable data source. So if people debate about it, if there are big changes, you will see them, and you can't miss them, and you think it can convince you relatively quickly. And then, of course, you can debate. I mean, it's more at the end. What matters, at least to most people, is that the forest is gone. It's not so much how much carbon is there. Carbon is also important, right? But at the end, it's about the forest, because the forest is not only about carbon. So if you can get well, and we can show that there are certain developments that are worth noticing, worth alerting about, I think we can support these things, and I think we should do that. That's our role also as researchers, as people claiming transparency, and with our open, I mean, this is an open science conference, right? In the open data group, we are kind of leading it. We look at other areas in inventory domains, forest inventory, agriculture inventory, surveying, stuff like that. I mean, our domain is so much more open and so much more transparent. We're almost leading the way. Let's see, then we have first question. Yeah. So, I mean, yeah. So, what I would say is this year there will be, as far as I'm aware, 3 or 4 10-meter global land cover data from different things. We have seen that in the land cover that happens because it's possible now. People try it. They're all, I would say, demonstration products, first time things. They are demonstrated to show that they have technology to do it. You can process Sentinel-2 and in some cases Sentinel-1 data operationally within a relatively short period to produce predictions at 10 meters for the whole globe. I think that's the big message. That's the good news across all of these 4 different products that are available. The one on Microsoft has been released. I think it's one of the first ones, the Chinese one. And it has also been heavily criticized because if you look at it, then that's what people do. They look at their backyard and then, of course, it's all these problems and things like that. And since there's no real well-done accuracy assessment with it, it's hard to say. I mean, and then that's sometimes what happens if you have these technology-driven products. It's relatively easy to produce a product. It's still an effort. But then how good it is, and then that's the first thing. Secondly, I mean, these are maybe 10 classes. And then that's always the problem we have with global. You have to have categories that work everywhere. And of course, you often lack local specificity and also local detail. If you want to have a map of the global solar farms, well, get some training data, process your data, and run an AI algorithm to predict the probability or the location of solar farms. It's if you have that very specific question, don't expect the global land cover map to do that with these classes. So if you have a very specific thing, do a very specific mapping or mapping of what we have, greenhouses or some, intersections of roads, or all these features, right? Or urban areas, so to say, or certain urban structures. You can go for these very specific things, and if you're interested in changing, well, then train an algorithm that can do these very specific things. Don't expect the global land cover data that are basically developed, first of all, as the demonstrator, secondly, also for a broad array of users to get in that level of detail. That was helpful. So, how do you avoid a paradox situation where we actually need a higher accuracy of land cover biomass in the past, but have better incentives for the future? In other words, we know a lot about today, but too little about past. Okay, good point. So, what if you have a situation we have better data today? For example, the 10-meter global land cover I just talked about is going to be available 2020, it might be able to go back a few years because the data are there, but then it will stop there. So that's something that's marked up for the future. But indeed, if you're interested to look further back in time, and I showed this one analysis where we had 60 years of land cover data, then of course you have to tap into different data sources. And then the question is really, how can one generate a consistent data set, and then let's say the lowest quality data determine the characteristics basically of that data set. So if you, for example, these long-term land cover data sets, it's the same as maybe for long-term biomass data sets, they're mostly developed for the climate and climate modeling community, which are okay at even 1 kilometers to detail, maybe so 0.1 degree, 0.25 degree resolution. But then you have more data of going back in time. You have the AVHR time series, some of the early data go back to 82. And then if you go before that, actually, they'll still use some ancillary data, proxies, historical maps, and all of that thing. So you start to get more into a modeling of changes rather than using those observation data. And so you can have then, based on the data sources, certain inconsistencies that can be done. And that depends on your use. If you're a climate modeler that needs a long time series of land cover change biomass, well, you can do the best possible for that purpose. A lot of the users, in fact, that we have are actually not so interested in us. Maybe they're interested in a few years, but if you talk about agriculture, forestry, I don't know, insurance, and all of that, they're a bit interested in the past, but they want data, high quality now, and as quickly as possible. And for that, it's actually fine. If you want to go back in time, be ready for some limitations and try to derive the most consistent data possible. Hopefully that helps. So that was a good question. So there are now 10-meter data already available, but the question is how much detail can we go while avoiding privacy issues? Right? And then the question is it an issue of the underlying data or the map? Because I would say the underlying data, and then it's not only about 10-meter data, but I mean, you have a commercial site that produces half-meter data for every place or almost for every place on the planet that you ask for. And Norway just funded an open planet archive for the whole tropics. So that's 3.5 to 4 meter data for everyone in the tropics monthly data. So you can zoom into a level of detail where you can really start to look at people's backyard. So I think there the issue is more with data, not so much with the map. The map is, it's a 10-meter pixel of maybe 10 classes. It tells you whether it's a house or whether it's open water or whether there's a tree there and stuff like that. So I don't think that's, at least on that scale, doesn't make a big problem. but it's more the data itself, because then everybody can see and interpret whatever the neighbor, they want to see with the neighbor. And then, of course, the issue of timeliness is very important, because who wants to look at an image of somewhere when it's a couple of years old? Maybe that's interesting in some cases, but we really have this data and reasonably up to date. Then I think it's not really trouble. So far, there have been some debates about that, but so far I have not heard anything big as we would have had a few years ago when Google Street View without the data, and where people would blank their houses, and then now they get people's faces out and license plates and all of that. We're not at that debate yet, I would say, on that level. And there will always be limitations for limits in front space. There are physical limitations. You're never going to get to that detail that somebody is providing. But it is a sensitive issue, and I think it will probably can come down to one bad case that makes the press and really shows that this can change, that can tip things. That's also why Copernicus tends to remain with 10 meters, maybe 5 meters in the future, not to also step on the feet of commercial providers, but at the level where it's still reasonably considered a safe zone.
Thank you so much. There's so much more to do.
Ciao Marcos.
We are switching the equipment. We continue in a second. You need a mouse. You can do like this with the time. You do like this. Yeah. Let's see. Can you all hear me? And somebody just please write in chat if you can hear me, the online participants. Okay.
Can you hear me? Online participants?
Yes. Okay. Everything's great. Okay.
Okay, this should help.
Okay. So go, please. 15 minutes, 5 minutes.
All right, I'll try to hurry up. Hello, everyone, and thanks again to Martin for such an inspiring lecture to try and follow up in an equally entertaining way. I'll try to do my best. As Martin said, any student can basically make a model and do some land cover classification. So, well, that's what we did. There's a lot of aspects that I will not go into, but I will try to tell you a bit about the model that we used to make the 20 years of land cover data that you can find in the GeoHarmonizer project. So just as a short schematic, we made one model in the EU map package that we have also that we're also going to be demonstrating in this workshop, and everything was done inside pre-processing, sample harmonization, the overlay to actually put all the training variables in the data, and eventually the classification. So we trained one model, more than 5 million harmonized training points from different data sets from over 8 different years with more than 200 Earth observation covariates to predict 33 classes, because as we just heard, having a high thematic resolution is makes it useful for more people. For 20 years, from the year 2000, at 30 meters resolution, because that's what was available. So this is a very big schematic. I'm not going to go into everything. We're actually just going to be talking about the model, which is here. So we are predicting 33 Korean land cover classes. But why would you want to do that? Because that legend is not really optimized for pixel-based classification based on remote sensing, because there's a mix of land cover, land use classes. Some of them are very heterogeneous, such as airports, for instance, because an airport, if you look at the map, it's just pixels of grassland, roads, and buildings. So how are you going to do that with pixels? Well, we still did it because CLC has many classes, and it's useful in more situations if you get the accuracy right. And also, if you feel uncomfortable about the accuracy of certain classes, you can just aggregate them because it's a hierarchical system, and those are pretty rare. And the goal of this project was not necessarily to get the highest accuracy value, even though that's of course quite nice, but to create a data set that is useful to as many people as possible. And that's also where some of the methodological steps we took come into play. So I keep saying one model, but it's not really one model, it's an ensemble, which means that it is actually a group of models that work together to make predictions. So this ensemble consists of 3 models: a random forest, gradient boosted trees model, and a neural network that we trained on the same training data set. And these all make predictions for every pixel that we try to classify on. Those predictions are fed into a logistic regression model, which we call a meta learner. And it learns from these predictions and tries to make a better prediction out of them. So it aggregates the predictions into one prediction per pixel. So this one ensemble is actually 4 models. So why would you want to do that? Why would you want to make it more complicated? Well, there's some advantages. These separate models that are part of this ensemble can learn in different ways, and they learn different parts of the feature space. And this meta learner understands, or ideally, which model performs best in which situations. And we tested this, whether that was the case in our case, and that's actually true. It's more than the sum of its parts. The ensemble performs better than any single of its component models. So under the hood, it kind of looks like this. You throw a bunch of Earth observation data into the ensemble. You train the ensemble. Then these component models, they predict the probability of each class. So in our case, 33 classes times 3 models is 99 probability values. These probability values are the input for our meta learner, not the actual Earth observation data. And then this meta learner predicts 1 probability for each class. And then the class with the highest probability is what we consider to be the most likely class to actually be there in that pixel. So these predictions are not 100% accurate. I will get to that later. We include uncertainty, and I will show you how we calculate it, to show where mistakes are more likely. This also makes it more useful to more people, because then they can see how reliable the data for a certain area is. And I will get to more of these advantages later. So some publications include uncertainty for their predictions, but they do not do it for every class, which we do. So as I said, the goal of this project was to make a data set that is useful to as many people as possible. And including this high thematic resolution, including these probabilities per class, and these uncertainty values that are available to everyone that accesses the platform, basically enables all users to make their own custom mapping efforts in this high thematic resolution and make their own estimates about how conservative they want to be with these uncertainty values, how reliable the map is for their specific use case. And that is what I would like to call honest mapping. So this uncertainty value, we calculate this uncertainty by taking the standard deviation of the three probability values per class. If all the probability values are high, there's not much difference. So the standard deviation is low. That means that the model is certain about that class. If they're all low, the model is also certain because it's just, well, every model thinks the class is not there. If you have diverse values, the standard deviation is high and the model is uncertain. So to expand this under the hood schematic, we have 33 classes with 3 models, which is 99 probability values, 3 probability values per class. And then so the standard deviation of 3 values is the uncertainty per class, and then this is a separate data set of the model uncertainty. So that's all really cool that we do all this extra effort to make it honest and make it diverse, like useful to a diverse user base. But does it actually work? Well, classifying 33 classes is difficult. That's also why hardly anyone really does it. And classifying the CLC legend is actually difficult. For instance, the example I gave earlier in this presentation about the airports. Then we also have the land use is not a land cover problem, and that CLC contains a mix. So our initial results were a little bit lower than the state of the art, considering the 33 classes. As you can see here in this really big confusion matrix, you see a big line, like a vertical line going down. A lot of classes are being incorrectly predicted as non-irrigated arable land because that's just a pretty big, diverse class. There's a lot of that in Europe, so the model was pretty biased to just think whenever it wasn't really sure, it's probably that one. Well, you should see the even bigger one I made. That's I didn't include that because it's a bit nightmarish, but then you also see a really big block here in the center, and that's all the kind of nature classes. Except for forests, the model had difficulty discerning different nature classes, basically. The point is, this legend is not useful for all users. So this is not the only thing that you should use to judge how well the model operates. Because if we aggregate to a higher level in the Korean land cover classification system, we have 14 classes. Still, for instance, now it's actually readable, I think, the codes on the matrix. This is urban fabric, industrial units, arable land, permanent crops, pastures, forests. Also my favorite class, scrubs and other vegetation, because it's a mess. And some water and wetlands things. You can see that the accuracy improves. And it's also more clear to see where actual mistakes are being made. For instance, non-forest classes are often still seen as arable land. Well, natural classes, it actually does okay, but the one class that is frequently incorrectly predicted there is scrub and other vegetation. This is actually because of one specific class. I'm just going to go back, and that class is transitional woodland shrub, because that's one of those complicated CLC classes that contains trees and shrubbery and grass, and it's just like a mix of things, and that's why it's confusing the model. But then if we go to the highest level of aggregation, you can actually see that just classifying nature and classifying agriculture actually goes pretty okay. It's still the biggest source of mistakes, but now the accuracy value is actually decently high, like higher than the benchmarks, like the thresholds for most products. Of course, this is a very low thematic resolution, and it's not an optimized legend. So for short, it kind of does work if you reduce the number of classes. Mistakes mostly happen within the same categories, and if you go up to a higher level, those mistakes become irrelevant. And the point is that not every mistake is relevant, or not every low-level class is relevant for every user. But I mentioned that this legend is also hard to classify. So we wondered what happens if you use a different legend altogether. We did not retrain the model, we just predicted in a different legend. We contacted Malinowski and his team, Radek Malinowski, a Polish researcher, who was kind enough to share the validation points that they used to map 13 classes in an optimized legend for pixel-based classification in a very interesting publication from last year. in this map, you can see where these test sites were. It was like a very systematic sample point gathering plan. And we transformed their legend to theirs. It was not perfect because some of their classes did not match ours and the other way around. So we made two comparisons. One optimistic comparison where all the points with true or predicted classes that were not in Malinowski's legend were omitted from the accuracy report. And one conservative one, which is, well, you could also say pessimistic, where all those points were counted as error. So anything that the model was not actually trained to do, which is, let's just say it's a mistake. So Malinowski et al., they reported a kappa score of 0.82, and we got that with the conservative estimate, and the optimistic estimate was actually higher. So that was good news, because that means that our model, which we threw a lot of data in and a lot of computing time, actually does work if you use a better legend. And it also shows that you can actually have a decent legend that is optimized for these types, and also that you can actually train a model on such a complex legend and it still performs well on an optimized legend. And that's what I find very interesting, because apparently training the model on such a weird legend, or at least for this use case, does not necessarily confuse the learning process. So you can just reclass those predictions to a more useful legend, and the values change. So that is promising also for the output of our model for any kind of use case for people that actually need a different legend. So in short, the model performs. It performs okay on the biggest classes in our current 33 class legend. It's similar to the state of the art, at least in single year land cover classification, if you adjust or optimize the legend. But as I said, we're not aiming for maximum accuracy, we're aiming for maximum usefulness. And so this high thematic resolution, plus the probabilities, plus the uncertainty, makes it customizable for many users. And so during some supervisor meetings, the accuracy score was mentioned, and it's a bit on the low side. So that's actually why we're now working on a 43 class version, because we don't care about accuracy, we care about usefulness. Well, I think I was actually also writing this during Martin's lecture, and I think the temporal consistency definitely needs improvement. I will show you some examples in a bit that shows this. A temporal accuracy assessment would also be very interesting. I would like to work on that. And of course, we do need to improve that accuracy, especially for the smaller classes. The fun thing is, however, that all this data is available online for anyone to see. So I would encourage everyone to actually check it out and see what needs improvement and tell us, because then we can do it. So now, how much time do I have left? 2 minutes. Okay, I'm just going to show one example of a place that is pretty close to where my mom lives in Portugal. Yeah. So this place is called Urbanization. I'm just going to show it in the data viewer. You can see it here, right? Yeah, Urbanization, Costa Azuri. Well, let's this. Can I move this screen share? Yeah. There we go. Okay. So let's just see what happens. Is there going to be urbanization here? Wow. That's some urbanization, right?
Some pixels you have like urbanization, and then it's green.
Yeah, but that's also why we have actually taken steps to improve the temporal consistency. They've just not arrived on the platform in that sense. But Chris will definitely show us all how he has enhanced that situation, right? Yeah. Second demo. All right, let's go back. So we also have this interesting use case of the L'Aquila region in Italy that we use to test some of our stuff. It actually shows an earthquake. And so this is where you want to look. We're gonna just move 1 year and poof, suddenly there's urban area. Of course, that's not really like an accurate prediction, but also you can see it's just transitional woodland shrub, one of my favorite classes, as I mentioned that. And then suddenly mineral extraction site. Well, that means that it's just an open earth like something that resembles a quarry, for instance, something that's caused by an earthquake. So we do not have earthquake damage sites in our legend, of course, but this is a close approximation. And then afterwards, the transitional woodland shrub is gone, and it's just natural grassland because, of course, it's regrowing. So this is an interesting example, I think. All right. Yeah, I'll check it. Matrices, yes. Nice paper. Oh, right. Question on YouTube. Oh, what did you find in Malinowski's classification scheme, which is different from your original classification scheme at various levels that improves your accuracy? Well, what we found was that a lot of artificial surfaces were aggregated, for instance. Bare soil is also aggregated, like from different classification, like from different lower level CLC categories, and they just combined it into one. Basically, they really looked at how it looks from space instead of what you want to do. I mean, I could see if I could find the classification retooling. No, I don't have data because it's not my computer. I will put that on. I will put that on Mattermost. I'll just share the whole reclassification scheme. It's also in a publication that's currently in review, but we have posted a preprint. I don't have a link here, but I will also post that one. And that also contains a lot of information about this. I hope that's a sufficient answer for now. All right. Okay, cool. Nice.
So we have a next presenter, also from the GeoHarmonizer project, Carmelo Bonanella, who worked on the forestry species, mapping the distribution of forestry species. So he's going to give us a talk, 20 minutes. Please leave 5 minutes for questions. He's also a PhD student and Open GeoHub.
And the maps dev is also maps. Okay. Where is Mattermost? Okay. Screen, yes, it's already shared. Perfect. Thanks. Okay, can you all hear me? Okay, can you see the slides? Perfect. Yes, as Tom mentioned, today we will talk about vegetation mapping. For those who followed the training session on Monday, we will be talking about vegetation mapping again. So I hope I won't bore you a lot with more of the theoretical stuff that I already mentioned. So if for everyone that is not familiar with species distribution modeling, which is the broad term to which we identify vegetation mapping, I will just talk a bit about the theory. It's not shared. Okay. Yeah, let me check that. Yeah. Yes. Whole screen. Yeah. One about. Yeah, it's here. Okay. I thought it was just already. Yep. Yeah, I mean, you didn't lose a lot. It was just a call. So yes, about the species distribution modeling, as I said, which is one of the techniques that we use to model the distribution, either potential or actual of different species. Could be vegetation, as in this case, for example, forests, or could be also mammals, other kind of species. Then we will focus on which data and which covariates we use to actually try to understand how these species occur on a European scale. I will give some details about the modeling that we used, which is very similar to what already Martijn showed us, and also some results in the development server as the demo that already Martijn showed us. So we talk about species distribution modeling on a correlative scale. So what we will do is just having a training data set with the occurrence of the species that we want to predict. And then we associate some values from different predicted variables to the location where we actually observe the species or not. We fit a model to estimate similarity between these sites. And then we predict on either space or space-time in the region that we are interested in, which in our case is Europe in terms of space, so the whole Europe, plus in terms of time on a time coverage that goes from 2000 to 2020. So let me also move this a bit so you can see. So basically what I was talking about is the difference between the potential distribution of a species and the actual distribution of a species. Here you can see on the left the geographical space, so how we actually find the species in the environment. So for example, here this is the area that considering all the conditions that we see in the environment, the species could live. And we can see that in gray is the area where the species is actually observed, while in white we can see that these are the areas where the species could potentially occur, but is not observed, either for example, problems in terms of migration, of moving of the species, or because this niche is already occupied by a more competitive species. So what we do is actually observe the different predictor variables that, well, theoretically speaking, would describe the distribution of the species and analyze them in the feature space and see how the species basically occur in this feature space. Okay. So this is, for example, one of the two outputs that we can get from species distribution modeling. We can get either a map that shows on a 0-1 scale where the species could occur. For example, here you can see this coming from the European Atlas of Forestry Species for the European beach. The green area is where the species could occur, while instead the area that is in yellow is the no data, so there are zeros, all the areas where the species does not occur. Or we can get probability values. So areas where the species could potentially occur for isobservability is values that come from 90 to 100% where the species could actually live and prosper, while instead all the other areas are the low probability values where the species does not occur. So what we did was during the last summer school, Johannes Heisey created this harmonized data set with all the 3 distribution points that we have available for Europe, coming from 3 different kinds of data sets: the National Forest Inventory dataset, the GBIF dataset, and also some Lucas points. The code is available online. The dataset is available on Zenodo. So if you want to use the same dataset to replicate our procedure, you can always do that. This is how the data looks like. So after we harmonize and put all together all these points, we have more than 3 million of points scattered across all Europe, divided by 70 different forestry species. And we can see that we have a higher number of points here in Spain compared to all the other countries. But actually, if we analyze how these points are distributed, we see that they are highly clusterized in some areas, while some areas, for example, have no survey or samples at all. So we face this problem by using the land cover products that Martijn was talking about. We created a forest mask for all 20 years that we are actually trying to study. And then we overlay the points from this data set with the forest mask. And all the points they show for all 20 years a high value of probability, so more than 19% in one of the classes that were put in the forest masks, then we will use as points for the modeling. So for example, you can see here that this is one of the points that we actually included in the dataset because it shows a high value of probability of coniferous forest. This is, for example, a Norway spruce that comes from a European National Forest Inventory dataset. It's located in Germany, while instead this point comes from the GBIF dataset, and we didn't include it because we can see that the values of probabilities for the classes that we put in the forest mask are very low across all 20 years. This instead an overview of the covariates that we use. We use different climatic covariates, both on a long-term scale and on a time series scale. Terrain covariates come from the DTMs or DTM derivatives. Then reflectance data that comes from Landsat. That's the same data set we also use for land cover data. And also maps that come from the European Forest Atlas to map the possibility of the same place being occupied by another species. So it's a way for us to include the interspecific competition between the species. This is how we face the clusterization of the points. So as we can see, for example, this is a cork oak, which is mostly located in Spain. And there are different clusters also in Sardinia or in Corsica. But we can see that among all the 300,000 points that we have as training data for this species, 1/3 of it was actually in one of the tile of 30 kilometers side that we use for tiling the whole Europe. So of course, this cluster can influence and possibly impair the models, and we can actually get very big biases in the distribution of the species. So what we did was actually checking the distribution of the points across all the tiles for all the species in Europe. And then we took a median that will be used as threshold value for how many points can be used in modeling in each tile. This is how the modeling looks like. So we first started testing different machine learning algorithms without parameter optimization or feature selection. And we trained these different models on a subset of species, testing also how the species in the presence data and the absence data will look like in terms of them, either the most occurring species, which were more like than 500,000 points, or very less occurring species, which can be less than 1,000 points across all Europe. And the 3 best learners that we got from the first, from this first part of the modeling were then used with a bigger sample, 5% of the training data set for all the species that we are trying to model, which at this point are 50. And we trained them on, and we fine-tuned them, and we trained them. And I can show you the feature selection process in a bit. The results, so the parameters that we got in the feature space for all these 3 learners were then used to train an ensemble model where we use a logistic regression as a meta learner. And we use a 70-30 split in the dataset. So we have 70% for each species used as training and 30% as test. And then we use 5-fold spatial cross-validation during the whole process. And the parameters that we use for the base learners of the ensemble model come from the phase 2. We then use everything. I didn't mention that everything here that you've seen is modeled using R, and especially the MLR framework. And for the feature selection, we use scikit-learn library in Python and we use log loss because we have different data set for different species. So the proportion between presence and absence data is constantly changing. And to avoid this uncertainty in how the probabilities can be predicted, we use log loss instead of overall accuracy or other metrics to assess how the features can be selected. So the process goes by using a random forest classifier with a 5-fold spatial cross-validation and recursive feature elimination. We checked the first dip in the values of log loss across all the covariates, and that's the value of the covariates that is used in each model for each species. To have consistency in this, we replicate this procedure 5 times for each species, and we then took the average of the number that we get in the first dip for each species. And now you can see how these maps looks like in the development server. They are not completely online. They will be online. I think by tomorrow, most of the species will be online. So you can also check by yourself. And that's how this species looks like. Yeah, this development server. Let me move this. So we can, for example, check the probability distribution for the Norway spruce, which is the same that was available in the slides. You can see the legend. The colors go from probabilities that are below 10% to 90%. We cover the whole Europe, and our time frame, as I mentioned, it goes from 2000 to 2019. So you can check somewhere like in the length cover classification points and check, for example, the probability distribution for a species to be there. We also have points available, so you can check. And we also have a compare tool where we can actually compare the actual distribution, which is modeled using reflectance. So you can actually exclude cities or also farming sites or other urban kind of land cover classification with instead probability distribution. As I mentioned in the show in one of the first slides, in the geographical space, usually the potential distribution is very much bigger than the actual distribution. And that's something that you can check here with the slider. As you can see, the condition for the species to be present in a specific area are already available for a lot of areas, while instead the actual distribution of the species is very much smaller. Yeah, because we do not include anything that does to do with urbanization or anthropization in the environment. So everything is basically excluded for the time frame that we are actually analyzing. Yeah, let's see, for example, Scandinavia. Here, for example, yes, we have the conditions for the Norway spruce to be present, but this is actually one of the species that is less occurring in the southernmost part of Sweden because it's mostly covered with broadleaves. Or, for example, you're in Germany, we can see that's the same, or in the Carpathians or the Alps. This area, for example. You can see the difference. And it's kind of makes sense, of course, because it's from expert knowledge, you can actually say that the top of the mountains or the glaciers is not an area where you would actually see the species or where the cities are. Yeah, so this have to turn off the comparison map. So as we said, we focus on usability of the maps. So what we actually provide is, okay, probability values for where one pixel, for example, can show the potential distribution, the actual distribution of one species. But we also provide for each layer an uncertainty map that shows, okay, should I use this value? Is it reliable or not? So we have a scale that here shows the variance based on the procedure that Tom explained in the first days of the training session. So we use a correction factor for the ensemble models to avoid, for example, the extrapolation problem that we talked about in the training sessions. So you can actually check for each pixel or each area that you're interested in, if the values that we provide have a high tolerance in terms of reliability or not. And I think that's about it. So if you have any question, please. Mm-hmm. Yep. Let's see in the chat. Nope. Anything on YouTube or Mothermost? Yeah.
Maybe I do a question of similar to mechanics problem. You can see that sometimes when you look at a fix, 1 year it's you know the probability high, the other year it's close to 0, and then it comes back again.
Yeah.
How do you prevent some people, you know, having like a communication that somebody tries to be in the time to be there?
On a long-term scale, we know that, for example, this is not possible. We also provide uncertainty maps, so we can say that that value for the specific year is probably due to noise, or also we can another thing that we can use on a long-term scale is actually remove the noise by using trend analysis. So that's also some post-processing that we could do. So we could provide potentially raw values for the maps and also post-processed maps. Oh, let's see. I see new messages in the chat. Yeah. Okay. Okay, there's a question from Pablo, which says, it is only possible to model part of the actual distribution if you consider abiotic, biotic, or movement limits. But do we use this kind of predictor after the feature selection optimization, and which variables are in there? Okay, so maybe something that wasn't clear during my presentation is that we don't have one model that models all the species. Each species has its own model, its feature selection, optimization, and part. So we have to check basically in every model which ones were used or not. But yes, for example, the abiotic and abiotic is always there. Like climatic variables are always in there. And we also can see the differences between high resolution layer that we use as predictors, for example, the DTMs or the slopes that are highly available, or for example, long-term abiotic covariates like the bioclim that have a very coarse resolution. Other things that pops up in terms of covariates for almost all the species is the reflectance data, especially for the actual distribution, because those can actually help us exclude all those areas that instead are covered by cities. And in the potential distribution, we also have some layers that come from the University of Maryland that show, for example, the barren areas of the Berland, and that for some species actually comes up as one of the first covariates. So we can actually exclude very quickly all the areas that do not show vegetation. But yes, when we will publish the paper, which is now in writing, we will provide like data for each model, and you can see which ones are the covariates that actually pops up at the most important for every species. Yeah, okay. Yeah, this is not a question, it's just an idea. Yeah. Yeah. Yeah, someone here in the chat was suggesting, for example, to connect with JRC. We try to do that, but they also have the same problem as us. The amount of points that are available to model these kind of things, the ones that we are using right now, this is the highest amount that's publicly available. I mean, just for yeah, it's possible. It's not a problem. We have the computing infrastructure to do that. It would be also wiser to not use all of the million of points that you were mentioning. Like we could use most of them to validate our maps, for example, which is looking for an independent data set in terms of trees, especially if you are modeling or forecasting, is always a problem. So using all these points, for example, as an independent data set in terms of sampling bias or everything, could be also useful to make the maps more accurate. Yeah, that's fine.
How can I use your results to help me decide which?
Yeah, basically that's a good question. You can first check the areas that you're interested in, And then in this area, you can check which ones of the species that we model have a high value of probability in terms of actual distribution. So from that, you can say, okay, these are the species that will actually do well in this area. And then based on your interest and on your time frame interest, so for example, if you want to have like short rotation forestry, or if you want to plant for like 100 years, and also what your interests are in, which kind of forest do you want? Is that just production? Do you have interest, for example, in protection of the area, for example, like forests that are planted high in the mountains to protect against snowfall and all these kind of problems? That depends, but yeah, you can for sure use the maps as having a kind of an overview of the trees that you can plant there. And then also competition plays a role.
Okay, thank you so much. Okay, usually,
We are starting in a second. For the people following online, we are just preparing to start. Yes. Let's see.
Just to make sure everything.
Okay, I think you're ready to go. Share. Yes, go for it.
Okay. I'm unmuted. Yes. Good morning. Here. Okay. Hi, good morning. I hope everybody is listening to me. And so I will present about a product that we are preparing in the context of the open data science and in the Open Geo Hub. So, and this product, one of the main applications of it is detecting land degradation. So I will explain about the workflow that we are implementing, what are the ways to access the data, and preliminary results that we have till now. So if you think in a degraded land, so I would like to start with the definition. So degraded land is a land that has lost some degree of natural productivity due to human caused process. So there is no like general definition or approved definition across this concept. So, but if you think, for example, for pasture land, a degradation over the pasture land, it's mainly when you have problems with the management and you will decrease the productivity in the land, and it will affect, for example, the livestock activity. But if you think in a forest degradation, so it's a different way to see the problem, and mainly it's related with this carbon stock. So it's a big problem today, and I'm not here to solve it at all, but I'm here to present one product that could help and that could enable users to deal with that. So, and Gibbs and Salmon, they did a comprehensive review about the topic, and they identified at least 3 ways to detect degradation in land. So expert opinion, satellite-derived net primary productivity, and biophysical models. So these 3 methods, they have different benefits and different limitations. And specifically for the satellite, we could have like a global consistent methodology and qualitative, readily, repeatedly, and we can associate these measures with potential change. And there are other limitations also, for example, mapping like degradation in soil, but it's a good starting point for to try to solve and deal with this problem. So mainly, if you think like in a satellite image, you can use, for example, the vegetation index products. We have several global products now available, and you can use it to actually analyze the time series, and you can understand how this NDVI is changing across the years, and you can correlate the NDVI with the primary productivity. And if you get this time series, and you can perform different analysis to understand it, but mainly what you need to work, you need to have a baseline, because degradation, you need to follow the process across the time and see if you are gaining or losing some of the signal. And of course, we have multiple sources of Earth observation data. We were discussing about it. And here we have example for modes, Landsat, Sentinel, and PlanetScope. They are different challenges to work with this data. But mainly we know that most part of this data is not real analysis ready. So they are not artifact or cloud free. They need to be gap filled, and some of these data are not really fully accessible, like via these new protocols like cloud optimized DOT for stack. And if you think in these three aspects together, we don't have like a product like that it's ready to go and you can access and retrieve, for example, a time series with this free of clouds and gap filled, and where you can really perform. Yes. Yeah. So, and considering that, considering that, yes, there is one more part here in the slide that's really important. So it's a nice podcast by Map Escaping that discuss that actually satellite data is not a commodity. So we have this view today that we have multiple sources and a lot of information outside, and we can, this information, this data is really collected and ready to go, but that's not the case in almost of these data, because you need to download, you need to organize, you need to pre-process this time series to really do some type of analysis. And to deal with this problem, what we are developing now is a workflow that process, we are testing it with modes first, but we have plans to implement with ProbaV and with Landsat. With Landsat, we already implemented in the scope of Open Data Science Europe, and my colleague Chris will present about it. But mainly what we are doing specifically for modes is we are accessing the Google Earth Engine, and we are removing all the clouds using this pixel reliability, and specifically for the product mode 13 key one. And this is a 16-day composite, so it's a level 3 product. So you already have like a lot of pre-processing this product to make it available and usable for the users. And we are aggregating it by 2 months. So we are putting together another level of temporal composite, and we are removing the outliers and gap filling time first and space later. And the output of this approach, we using this ready to go data, this analysis ready data, we are calculating a trend analysis to analyze only the trend component, but removing the seasonality that it's really important for example, pasture or savannas, where you have high correlation with the NDVI signal with the precipitation data. But also we are providing a snapshot of our workflow. So each of these parts of the workflow, we are putting it available. So we are delivering one way to do this trend analysis, but the goal here is really enable other users to work with this data in the easy way and to access it and do, for example, different ways to implement the approach and detect, for example, the land degradation. So this is an example of what we retrieved from Google Earth Engine, and you can see we still have a lot of gaps. This is a Modes is a great product, but even aggregating it for 2 months, we still have some gaps. And after a lot of computational, we produced it. So mainly, this is a gap-filled product aggregated by 2 months, and it's full resolution here, and we took the EVI data here. It's better to analyze, for example, crop, and it has less saturation for high values, like really conserved forests and different types of land cover, where you have like a high NDVI value. Here you have a less saturation with the EVI. So, and here we are seeing this time series, and it's basically, we can see that the seasonality of the planet, and mainly this it's more like an intra-annual signal. So using this data, we performed like this. This is a classical method to remove the seasonality and actually separate the signal in trend, season, and noise and residuals here in this plot. And if we get just this trend, so we will remove this seasonality aspect and this correlation with the precipitation, that it's mainly the response of the vegetation to the precipitation. You can see the same result, and now this is animation. So you can see that it's slowing, it's changing like during the years. And what we are doing actually it's analyzing this data to derive like the slope and the intercept, and basically a linear regression for each pixel of the planet, considering the modes data. And here you have the beginning and the end of this trend signal, and you can see some difference. And this is the result. So mainly we trained like one linear model for each pixel. And with this linear model, we have different statistics. So we can derive the slope, we can derive the intercept, and specifically here we are seeing the slope. So where we have like green values, it's mainly we have like an increased trend considering the whole period. So this is important. We executed it for 2000 to 2020. So if you change, for example, this interval for 2010 to 2020, for example, probably the result it will be different. But you can use the gap filled data. So the goal here is really enable other applications to work with this data and not specifically use the final result of our analysis. And in the pink, we can see where we are, where the EVI is decreasing. So here is an example for Europe. We can see in France. So I'm not quite familiar with this area, but if you look in this area, you can see that there is a decrease in the NDVI, and we can see it for this image. So this is more like a summary of the whole time series. You can think like that. And if you get 2 pixels in this area, you can see like where you have a positive trend. And if you analyze the time series, you can actually see that there is a positive trend. And you can see the original time series, the gap filled that we are putting available also. And you can see the negative trend for these areas in pink. We can go to other places. So I know this better, Brazil. And in Brazil, we can see some of the deforested areas in the Amazon forest. And we can do the same analysis. And the first time series, it's an increase in the NDVI, and mainly it's because knowing this area, it was pastury and was converted for cropland, for example. And in the opposite, the decreasing time series here was like forests converted to pastury and later to convert to cropland. So you need to consider that you could have different land cover transitions here, and it will impact in your analysis. But if you plan, for example, take this product and just analyze what are the stable, the trend signal for the stable class, we have land cover products that will allow us to do it. So you can work with just stable areas where were not was not identified none of land cover transitions. And here it's in China. So you can see And in China, we can see the same two examples, and mainly where we had like urbanization, and maybe I'm guessing here, but maybe it's a gain in productivity considering like a crop area. But what is really important, we want to provide this product to do like other type of analysis. So here it's an example of, actually this is an animation. I don't know why it's not working, but we provided this product for one of our colleagues in Brazil, and now they are using it to map in pasture land degradation in pasture land. So basically they have their own approach, and they are using this filtered time series and mainly analyze it across different years and normalize and integrate it here, for example, with a pasture map produced with Landsat. So that's the main goal actually in produce this type of data. So the next steps, this is we are working this product, so we'll run one more time because we found some artifacts and some problems in our workflow. So we will produce a new version, and we will put available as cloud optimized GeoTIFF to everyone access through S3. So we presented, for example, in these training sessions in this week, we presented how you can, for example, access one of these files, and I'm talking here like a global file. So it's actually a big GeoTIFF where you can just do a query and retrieve part of, I don't know, any part of the world, but you can retrieve part of Brazil and do your work with that. So we really want to provide it as cloud optimized GeoTIFF to enable the users to access it and do their own analysis, but also the result of the analysis and the time series, we will host it in the Open Land Map, that it's a nice viewer where you can analyze the result and have like a better idea of what we are producing. So we need to discuss some possible validation strategies for the results that we are seeing here, and it's really difficult because it's not easy found points where you have like reference points for land degradation, and we are open to suggestions. And we are working also in a publication, and the plan is when we have this workflow really ready to go and validated, we want to scale up to ProbaV and Landsat. And just to explain to you, this is a kind of problem that we have when you are working with the satellite data. So this is a ProbaV, it's a great data. But if you look, for example, what we have available in Google Earth Engine, I checked it also in the Vito web portal, from August 2020, we just have this part of the world. So this data, it's nice, it's there, but you need to be aware that even to work with it and to start running the analysis, there is a lot of work, a lot of pre-processing, and our goal here is really help in this direction and provide a data that it's ready to do analysis for different kind of applications. Okay. So the question is why we not use BFAST and why we are using this ordinary least square algorithm. And we can use BFAST, and it's nice. Now we have a nice implementation of BFAST, call it BFAST Lite, and it will be presented here. And the advantage of the BFAST, it's really you can now with the BFAST you can detect the breakpoints, so it works for different when you have land cover change, but mainly there are, if you think in generate like an image for the BFast, there are some difficulties. For example, you have a breakpoint and you have like a trend before the breakpoint and a trend after the breakpoint. So definitely we can use BFast, but we will provide more output because maybe you have 3 breakpoints and you have different trend signals between these breakpoints, and we need to save, for example, the slope, the intercept, where the breakpoint occurred. So there is this challenge here, and the problem. Yeah, the multi-source, now we are dealing with this problem separately, and of course they could be different, but mainly the best way to deal with that is do harmonization process before. And so, for example, here we are filling the data modes, doing like modes data, but from different data. So if we have a harmonization process to put all these pixels in the same like range, in the same scale, and really harmonize them, we can get fill, for example, modes with the Landsat or the opposite. But this is a whole process, so it's a whole project, and I think there is this possibility, but okay.
We continue with Lukasz Pavlik from the University of Silesia in Katowice. Keep us the slides here, just a second. We're just connecting. So you ready to go? Microphone is set. Yeah, you're ready.
Great, thank you, Tom. Hello, everyone. Can you hear me? I am.
Okay, now you're ready to go.
Okay, thank you, everyone. My name is Lukasz Pavlik, and I currently work as an associate professor at the University of Silesia in Poland. And this is just a small project developed in cooperation with Professor Sandy Harrison from the University of Reading, UK. And the project is still in progress, so we hope to improve it in the near future. This is modeling and prediction of wind damage in the forest ecosystem of the Sudety Mountains in one region in Poland, southwestern part of Poland. So first of all, I'd like to tell you a bit about the motivations. This region is particularly susceptible to forest damage due to strong wind, and one of the reasons for this particular susceptibility is complex forest history. Forests were largely changed in this part of Poland due to human impact. First, it was deforestation for agricultural purposes, and then in the last 2 centuries, it was intensive forest management, different practices, which resulted in changes in forest structure. So basically, in this region, processes were introduced in large amount, and this dominated forests. this region, these 3 species dominated the forest. So basically, we deal in this project with managed forests. And this project is linked with a concept of biomorphodynamics. So it is we try to look at how living organisms, and in this case trees, how they impact geomorphic processes on hill slopes and soil development. And the last thing, no past attempts have been made in terms of forest damage modeling using machine learning methods. Some objectives. First, the most important question is where are forests most susceptible to hurricane wind of different origin? And of course, it would be really useful to find potential strong predictors of forest damage caused by wind. So we tested several machine learning methods, and we selected the best models, and then we tried to build a map of damage probability. Here's our study region. This southwestern part of Poland is Sudeten mountain range, and part of this mountain range is on Polish territory, and it is a part of Bohemian Massif. As you can see, conifer forests dominate this area, especially spruces. A large part of this area was deforested. And some important information about climate, especially wind climate of this area. Here on this plot, you can see daily mid-daily wind speed, so you can see some seasonal component, but it is even better visible on this plot where you have number of hours per day with wind speed over 10 meters, over 10 meters per second. And here this seasonal component is even better visible. Basically, the highest wind speed is winter season, is in winter season, and it is correlated or related to extratropical cyclone events. Here you can see some examples from 2 regions. This is the highest part of the Sudeten Mountains, the Karkonosze Mountains. You can see some forest changes caused by strong wind in selected plots from 2001 to 2012 based on orthophoto maps. And here another example from the middle part of the Sudeten Mountains, and this damage was caused by the Kiel windstorm in 2007. So our workflow was like combining 3 data sets. First one, forest features before damage obtained from forest stays. And then based on unique ID number, we combined it with forest damage from 2004 and 2010. And this information was in cubic meters per basic forest unit. And then we try to fill it with some environmental predictors. Basically, bioclimate features from CHELSA database, from World Clean, and that was monthly, min-monthly wind speed, and then some terrain properties. We use shuttle radar topography mission product, and then we calculate some terrain properties in the Sagacz areas. So basically, we try to test it in 4 scenarios. First 2, we divided, or we use all 3 species versus only spruces. And then in another 2 scenarios, we use damage in cubic meters versus damage in cubic meters per hectares. And then these values, this information, we transform to binary data, and we try to use machine learning models to solve classification problem. Tools, mostly it was a CARD or package, and then we prepare maps in Quantum.js, and for some terrain features we use Sagacz.js. And for some parallel computing, we use infrastructure from PL Grid. This is sort of computer clusters and we use one of them with 24 cores just to speed up computing. So this is a list of machine learning models we try to test, and some on this slide is some information about hyperparameter tuning. So we try to apply grid search in order to choose the best hyperparameters and then to obtain the best model for our project. Before model training, we removed the highly correlated variables. So when two variables were highly correlated, so the absolute correlation coefficient was over 0.75, one of these variables was removed, but that was based on the relationship with other variables. And then we split our data set to training and test set, but just for years 2007, 2010, and other years were used as additional test sets for model validation. And depending on scenario, we could use from over 37,000 observations to 20,000 observations. And for model validation, we use 10-fold cross validation repeated five times. And here on this PCA plot, you can see the final number and relationship between variables chosen for the first two scenarios. So we had like only 11 variables. And you can see that even after removing some highly correlated variables, still some of them were closely related. Okay, now it's time for some results. This is for the first scenario. We use forest damage in cubic meters for all tree species. And generally speaking, this is a classification problem. So for evaluation of these models, we use accuracy and area under the curve, receiver operator characteristic curve. And generally speaking, results are quite similar. So for most of the models, the accuracy area under the curve is slightly below 0.7 or slightly over 0.7. And the best models, the best predictive power was offered by random forest model and gradient machine. And in this plot down here, you can see that the results were quite similar, and the best accuracy, the best predictive power was offered by random forest and gradient boosting machine for the first scenario. In terms of feature importance, tree volume and tree age were the most important features. That was especially for, I mean, generally for all models, but especially for the random forest and for gradient boosting machine. And some other variables like bioclimate variables were quite important. For example, precipitation over the coldest quarter or mean wind speed. And as you can see, topographic variables were less important. Okay, another slide. Using accumulated local effects plots, we can show how individual variables influence damage probability. So, as mentioned before, tree volume and tree age is the most important variables, and damage probability increase according to this result, increase with tree volume, tree age, but only for some age class between maybe 70 years old up to 110 years old. And further, damage probability increases with wind exposition index, topographic wetness index, but just to a certain threshold level, and then valley depth. Okay, so the final product was were maps of damage probability, and I'm not going to explain this in detail. It's much, I think, much complicated. But what you can see that damage probability for years 1998 and 2006 much higher than for 2020. Those two maps are made based on the random forest model, and this difference between years is even better visible for gradient boosting machine. So now, important question is why you have these differences, and we still try to find the best explanation. But maybe two reasons are important to highlight here. First of all, proportion of spruces for 2020 was less, for the recent data was less than for data between 1998 and 2006. But we know that spruces are most susceptible to damage to high winds. So it might be a good explanation that with lower proportion of spruces, we can expect lower damage probability. And another important argument would be changes in age classes. As you can see, that was quite on this density plot. It's quite well visible changes between 3 age classes between previous period and recent data from 2020. And as accumulation, local effectors show that damage probability was increasing for 3 age class between 70 and 110 years. Okay, now it's time for some conclusions. We tested 5 machine learning models for 4 scenarios. The most important predictors were tree volume and tree age. Geomorphic and climate predictors were less important, and 2 models offered the best predictive power. It was random forest algorithm and gradient boosting machine. And forest stand features might significantly influence probability of forest damage. Thank you for your attention.
Are there any questions? Questions?
Yes. Yeah, because we have this data. This data is in it was in vector layer data, so we could. Yes, yes, a vector map. Yeah. This is yeah, of course, yeah. Yeah, we didn't test it, the accuracy. I mean, in terms of yeah, specific parameters, yes. Previous analysis or yeah, of course. I mean, yeah, I wanted to say that the next steps would include some things we learned during this session. So it would be great to do that. Yeah.
But you have to give me the microphone, sorry. Panos, can you hear me? I need to make Panos.
Yes, I can hear you. Yes.
Okay,
You hear me?
fantastic. Just a second, I will add you as the. I have to.
Can I share the screen?
Yes, and I'm making you now. You're a co-host. Yes. So
Okay,
I will just
put the
introduce
screen.
you, Panos. Just give me a second.
Just tell me, Tom. Just tell me if you confirm if you share the screen. My screen. Share
Yes,
the screen.
we hear you and we can see your screen. Everything looks good.
Perfect.
Just to introduce you, so with us we have Panos Panagos from the European Soil Data Center, from the European Commission Joint Research Center in Italy. We are very happy to have Panos is my ex-colleague, and we are still collaborating. And I know they're very active. They have a lot of results, lot of publications, and very relevant for also our workshop. And a lot of data they produce is open. And we build up, GeoHarmonizer project builds up on the Lucas project, etc. So we wouldn't be able to do work without the product of GRC. And with this thing, Panos, I give you stage. You have 40 minutes. Please keep some time for questions. I hope you followed the previous sessions. There's lots of questions, lots of interesting discussions. So please take over, Panos. You're ready to go.
Thank you, Tom. It is my pleasure to be here. As you say, we are ex-colleagues. We know each other very well, and we hope to continue to collaborate because we do really interesting things. And I follow this morning the presentations, and really they are exciting for me. Just to warn you that my presentation will be a little bit. We'll have a lot of data. We'll present all the data sets most of the data sets that we produce here, and we produce quite a lot. But I will put them in a policy context. I mean that we don't produce just to produce, but we produce them in order to support various policies in the European Union. Just to introduce myself, I'm working in the European Commission in the Joint Research Center. We do research for policy. And today my topic will have to do with the modeling and mapping soil properties at the European Union. A small introduction from our side, who we are, what is this body, the Joint Research Center. The main policies that drive our research, which have to do with the soil thematic strategy, the European Green Deal, the Common Agricultural Policy, the soils in Horizon Europe and the emissions, the recent launched EU Soil Observatory. I will present some examples of data sets like soil erosion, land degradation, which are my competencies, climate change and soil organic carbon, diffuse soil pollution. Of course, all these have to do with the Lucas dataset, are produced mainly by Lucas. And I will give a flavor of what we are doing as well at global scale. So who we are, I will try to be sorry for this, but somehow you have to know who we are and why we do this kind of work. So the first slides will be a little bit dry, and they will have to do with policy, but the next slides after the 10 first ones, I'm promising that I will give you some exciting results. So we are a policy relevant organization. I mean that we provide science evidence results to our colleagues in Brussels in order to design the European Union policies. So GRC as a body try to anticipate the emerging issues, to understand the complexities, and to bridge the silos between different policies. Of course, we have to address challenges in the research, and very fast some facts and figures from ourselves, starting from clockwise. From the right, we are located in 6 locations in EU, in Italy, Belgium, Germany, Netherlands, and Spain. The headquarters are in Brussels, but I'm located in ISPA, which is the biggest GSE site. Important, we have to be policy neutral, not to be influenced by member states. I mean, we have to do to produce our results without any influence from various groups or various pressure teams or member states or politics. We have 42 large-scale research facilities and more than 110 online databases. 83% of the staff has a PhD, over 1,400 scientific publications per year. More than 100 economic and biophysical models are produced here. 125, I'll give you an example, instances of policy support per year we produce. 30% of our activities have to do with policy preparation and 70% with implementation, monitoring of the policies. We have a budget of 380 million euro and 62 million euro are earned budget from Horizon Europe or other research activities. So in practice, you see here a very complex diagram, how we try from a lot of source of info, web, models, best scientific practices, try to crowd source data from citizens, industry, expert knowledge, database, industrial knowledge, somehow to streamline all this through various processes in order to give some results and some advice to policymakers. This is our one of the main important roles. I think it's unique at this scale because we operate at the continent scale, and as I told you, we have to put all this information somehow in order to produce the best policy information. Just the themes that we deal with have to do with energy. There are 10 priority nexus: energy and transport, education skills, innovation systems, food and nutrition and health. I'm dealing in the thing on resource scarcity, climate change and sustainability, people governance, civil security, data and digital transformation, migration, economy, finance and markets. I'm going directly to our subject that has to do with land degradation and soils. Soils, we can say it's not a fancy thing. It's not something very fancy that can attract people. Climate change or biodiversity is a very nice thing, and we see that easily attract the policymakers. So we have quite a difficult job to convince the policymaker that soil is important. It's important for climate change. It's important for food security, and we have to do. Recently, we have seen recent events like the ones in Germany with extreme floods. You can see here some farms, as well what's happening on if we have high incidence of soil erosion, floods in Germany. For example, the land degradation can take place either with an immediate event like an intense storms or a flood, but can be a long time process, like you can see on the screen, on the picture from my hometown close to Larsa in Greece, or camp, where a farmer cultivates his farm for 50 years, and you see the difference of 1 meter depth between the two farms. This means inappropriate practices by humans to destroy our soils. So the main policy minister currently now in EU is the soil thematic strategy, which will have a new thematic strategy in 2021, in autumn 2021. We're preparing, we're working on this. But according to the existing one, the main threats on soils are erosion, the loss of organic matter, the contamination, the biodiversity loss, the soil thinning, the landslides, the salinization, the compaction. Therefore, we as experts, as modelers here, we have to provide policy support in those subjects for our colleagues. Not so much happened during the last 20 years regarding soils, and I can say that it was one of the things that was somehow neglected, but in EU, in relevant policies. Okay, there was the soil thematic study in 2006. Before, maybe we have seen some notions, notion about agricultural environmental condition in the common agricultural policy. But after 2013, we see some interest from the common agricultural policy about soils. We have seen the sustainable development goals to include the life on land and on how to combat desertification, a specific objective out of the 17 objectives regarding to soils. And now we see a lot of movements and a lot of discussion about soil, starting with the common agricultural policy, the future common agricultural policy, and the European EU Green, as I will tell you just now. So these are the 8 objectives of the EU Green Deal, and as you see, out of the 8 objectives, the one in brown are relevant to soils. For example, they increase the EU climate ambition 2030 and 50, and soil we know that has a carbon pool. The soils in the circular economy, because mobilizing industry for a clean and circular economy includes somehow aspects of soils. A zero pollution ambition for a toxic environment, the soil contamination is much relevant here. The biodiversity strategy, which has also objective to preserve and restore ecosystems and biodiversity, is fully linked to soil biodiversity. And of course, the farm to fork strategy, which has an objective for a fair, healthy, and environmental friendly food system. Here we have to model and to give information about nutrient excess, fertilizer, etc. So we see that soils are a cross-cutting theme within the EU Green Deal. Therefore, last summer, with Luca Montanello, we had an idea to start positioning how soils are important in this EU Green Deal. And below you can see some issues relevant to soil. We know that erosion is 2 times higher than soil formation, so we have an issue there. So we lose soil. The carbon stocks are decreasing and are reduced during the last years, and especially in peatlands. The earthworms and the biodiversity is affected by land use intensity. We see important issues about cadmium in fertilizers and copper in vinegars. So we speak about contamination. 23% of EU soils have critical densities, so soil compaction. And of course, we seal our soil because we build cities and we expand out to various other environments. So it's an important threat. So there we try to link all those aspects with the main objectives of the EU Green, which have to do, for example, in the EU 2030 biodiversity strategy, we have to put 30% of the land in as protected area. We have to plant 33 billion trees to increase organic carbon, to reduce the use of hazardous pesticides, nutrient losses, and of course, how to reduce CO2 emissions in relation to climate law. We have an important other policy initiative which have to do with soils in Horizon Europe and missions. Soil is one out of the 5 missions currently recognized in Horizon Europe. The other one have to do with cancer, with healthy oceans, with climate neutral. So this gives us the opportunity somehow for the next years to have quite a big budget for research, and this is very important for research activities in EU. And I'm going directly to our activities, which have to do with the recently launched EU Soil Observatory, and there we have 5 main goals, starting from goal 1 to develop an EU-wide soil information system, to goal 2 to have a stronger European soil data center. We operate currently European soil data center, where we want a stronger one. Goal 3 to monitor soil-related policies, which of course do our activities, but in relation to various policies within the EU Green Deal and the Common Agricultural Policy. Of course, the goal 4 to support the research and innovation, and the goal 5 to involve the citizens and to have a forum where all these issues take place and discussion takes place about the soil-related issues. Therefore, we produce large data sets. You may be aware of some of them because they are publicly available in the European Soil Data Center. And our basis for this is the Lucas that I will present in a few minutes. So our objective is to create, for a monitor system, to create a EU monitoring system which includes physical, chemical, and biological soil properties. For the moment, we model them with Lucas. We model the coarse fragments, the particle size distribution, the pH, the organic carbon, the carbon content, the total nitrogen, the phosphorus content, calcium exchange capacity, heavy metals. For most of them, we provide maps. There are the recent publication of Balabi 2019 in Geoderma with the chemical properties and the physical properties 2016 will provide information. Of course, we have we're ambitious and we have other objectives. So we want to provide information, such kind of data sets for pesticides, for biodiversity like nematoids, from fungicides, herbicides, antibiotics, and soil biodiversity. All this, we hope that can take place with Lucas, because Lucas is a component that is enriched with many other properties. I will go to soil erosion and give you some examples, because we have, from one side, the activities, the modeling activities which take place have as a basis the Lucas, but also we do other modeling activities with an empirical or process-based model. And one empirical model is the Rusle, which allows us to estimate the soil loss by water erosion in EU, takes as input parameters the soil erodibility, the rainfall erosivity, the slope length and steepness, the cover management, and support practices. Based on this, we produce the soil loss by water erosion in EU, and we monitor somehow erosion with these modeling activities, and we see that the erosion is much higher than the soil formation rate. So if the soil formation rate is considered around 1.4 and 2 tons per hectare, the soil erosion currently, the mean soil erosion in EU is 245 tons per hectare per year. Therefore, for 25% of EU soils, we have non-sustainable erosion rates, and we have something to do. And of course, this is our role here to provide policy advice to our policymakers to say, look, we have problem there. Those are the hot spots, and please introduce those, the X or Y management practice in order to reduce erosion. This may happen somehow during the last years because we have seen in the common agricultural policy there are more and more management practices introduced and incentivized, which somehow allow to decrease erosion in EU. And which are those management practices? You see the farmers on the top part, you see the crop distribution. There are crops which are less erosive, the permanent grassland, the alfalfa, the wheat, but crops which are much more erosive, like the sugar beets or the tobacco. On the other, on the bottom part, you can see the main practice that we advise that can have an important impact in reducing erosion, like reduced tillage, the plant residues, the cover crops, the stone walls, the grass management, the contour farming. Those are recommended in specific areas of EU or if you have got hotspots in order to reduce erosion. Of course, this map is not just for scientific purposes. We have done a lot of publication on this, but is used for developing indicators for policy support. As I told you, one of the main initiatives in EU was the United Nations Sustainable Development Goals, and this map fits one of the indicators there. We monitor the common agricultural policy till now, and we provide CAP context indicators. We plan the future common agricultural policy, and we do run scenarios. This map is taken also by the European Parliament Green Group, various statistics in Eurostat, regional statistics, of course, for the agricultural outlook that the DG Agri provides, and of course by various organizations, international organizations like the OECD, the IPBES, the UNEP, and the UNCD. We'll collaborate quite a lot with those. Of course, soil erosion is not just what the soil is eroded from the field, but how much of this soil is end to the river basin or to the sea. And there we apply another process-based model, which is the Rotterdam sediment, and we want to see the transport of soil sediments to river basin. And we see that almost 16% of the eroded soil is finished to the river basin. This takes place by calibrated 25 catchments, and of course, in this modeling approach, we should take into account that we don't model yet the other processes like gully erosion on landslides. This was a process empirical model that we estimate erosion, but we want to go much further, and much further means that we want to include the latest developments in Copernicus, which have to do with remote sensing and phenological changes in crops. So currently, we are able with Copernicus somehow to see the crops at the field scale, and we want to produce those, taking as inputs those digital land maps to know exactly where is cultivated what, because it's important for us. You remember my screen when I told you the crops have different erosivity inputs, and based on and phenological and take also into account phenological cycle, because the crop is different in Germany. The wheat is the phenological cycle is much different in Germany than in Greece, and with object-oriented approach, we want to produce a much more dynamic approach to estimate erosion on a field scale basis and on a yearly basis. And this will take place with Copernicus, taking also intra-annual variability. And of course, this allows us to run some climate and land use scenarios, which are very important for policy. So now we work towards this direction. Lucas, as I gave you a notion before. What is Lucas? Lucas is the biggest EU survey that was a nice proposal in 2000, early when Tom was there, 2006, 2007 in GRC, and we proposed in Eurostat. USAT has a monitoring monitors the land use changes with Lucas in EU. Every 3 years, surveyors go in the field and see the land use. But we have the idea, why not to monitor the soils? I mean, you take a sample from the soil field, you analyze it, immediately you have excellent results. So we start this exercise in 2009. We collected 20,000 samples. And based on this exercise of 20,000 samples, we have produced a lot of results. And then we see that this exercise is successful. We repeat 2015. So again, the 2015 data are available as point data. And now we repeat in 2018. The 2018 data are expected quite soon. And as I told you, it's a dynamic component because in the first Lucas, we had only the physical and chemical distribution, I mean, chemical properties. Then we added analysis on spectra. Then we added analysis on heavy metals. Now for 2018, it's very interesting to see the biodiversity aspects and the DNA analysis. Now the policymakers ask to have some analysis on pesticides and various and microplastics. So Lucas is a dynamic component that allows us to it is well seen by the policymakers as well. Has also some advantages that we assure data harmonization comparability. I mean, you don't have, we have experience in the past before arriving in Lucas, that we had different other surveys like IPC Forest, where different samples were coming from different member states with different depths, analyzed by different laboratories, and of course they were not comparable. But at least Lucas, we follow a standard methodology. We have a harmonized methodology. Points are repeated. Most of the points, 70% of the points are repeated. And we analyze them by one laboratory which is certified, and somehow the results are comparable. We have as our objective to collaborate with member states and to see to have better representativity of Lucas, to increase the number of points. This is really not easy. And now, of course, the Lucas allows us to cross-validate the results of our models. Important that you don't have only Lucas soils, as I told you. You have also other information related to this. You have, as the surveyor goes there, he knows the crop, he knows if there are management practices, he knows the tree coverage, he knows issues about biodiversity. So there are important info that are linked to Lucas, which are used by us to see what are the main drivers for having some trends in soil properties. It's a systematic approach, and our vision is to have not only 22,000 points, but 250,000 points. We discussed this in the launch of the EU Soil Observatory, and we hope that we see some good response from the member states, because of course doing this exercise is quite heavy for us and requires a lot of resources. Of course, the last objective is to integrate all these, the Lucas, with national soil monitoring system, because we know that France has its own monitoring system, has its own Lucas, something like Lucas, and we want somehow to integrate those points that we survey with their surveyed points, and somehow to have a convergence on how we do the analysis, how do the survey, in order to provide the scientific community much more data sets. About soil organic carbon and Green Deal, I mean, now the soil organic carbon is important for, as you know, the soil organic carbon is important because for climate change. Forests, we know that's a carbon sink, but agriculture emits 10% of the total EU greenhouse gas emissions. So therefore, we have to somehow to provide some estimations how we can decrease this trend, and we don't see any decrease in trend, unfortunately. I mean, the emissions coming from agriculture are stable or increasing. So we need to reduce the non-CO2 emissions and sequester carbon in soils. We know that soils with certain practice can sequester carbon. And in this context, in GSU we have developed a modeling platform, the Century Modeling Platform, developed by Le Gaff et al. And describing global change biology, where with the Lucas points as well included, we try to estimate the soil organic carbon in EU, and we see that in topsoil around 17.6 gigatons of SOC are included. Important to see also the scenario analysis. I mean, if you follow one practice or another practice, what will happen in soil organic carbon? So therefore, we run some scenarios like the conversion from arable to grassland, the crop residues, the reduced tillage, the combined residue and incorporation of reduced tillage, the laying rotation, the cover crop. So we see what will be the impact of following one X or Y practice in soil organic carbon. And this is important in order to propose to the policymakers which is the best practice. Of course, you propose, but you don't know if this is efficient, because our proposal will be to convert most of the Arabic grassland, but this is not possible because then you create other issues relevant to food security. So our objective here in GSE is not only to have separate silos like modeling erosion, modeling soil organic carbon, but somehow to integrate them. An important issue to couple our erosion estimates with the century biochemical model to see, how much carbon is eroded, how much carbon we lose with soil erosion processes. And we have done this in an integrated platform, and we try to estimate how much carbon will be lost. And we see that 76% of EU agricultural soils are losing very small part of carbon. Of course, there are some hotspots where carbon is lost, and we know that agricultural practices are important to prevent this reduction of erosion and to maintain soil productivity by maintaining soil organic carbon. There is an important debate about erosion and carbon cycle, if erosion is a carbon sink or a carbon source. There is quite a big debate on the literature on this topic. And we have seen various studies, one claiming one side that carbon is a sink, other claiming that it's a source. On our side, somehow we try to estimate the impact of human activities and the erosion effects on productivity and soil respiration. And we try to see what will be the future rainfall erosivity. Rainfall erosivity is an important factor that affects soil erosion in the future. And we know that we'll have more storms, more rainfall intensity that will increase soil erosion. So we try to see the impact of this natural process in increasing carbon losses in EU. And we have run various scenarios with the accelerated or current soil erosion scenarios. This was published by Lugato in Science Advances in 2018. An important policy that drives our work, both in soil erosion, carbon, and other soil properties on soil, Lucas, is the Common Agricultural Policy. And we see now that the Common Agricultural Policy has a new setup for the future. The EU now, we set some specific objectives, like we want sustainable development, we want a climate change mitigation. Those are translated in specific scenarios. So for the first time, we have soil relevant impact indicators in the Common Agricultural Policy, like how to reduce soil erosion with the percentage of land in moderate and severe soil erosion in agricultural land. It has carbon sequestration, which increase the soil organic carbon. And then we have to propose specific best agricultural environmental conditions in the Common Agricultural Policy. Which are the best practices to increase carbon and to reduce erosion. And among them, you can see to protect the carbon-rich soils, to maintain the soil organic matter, to be careful using some tools on nutrient controls, some minimum land management which has to do with tillage management, and the protection of soils in winter, the preserve of soil potential and the crop rotation. I will go very fast in soil contamination because we have done some nice work here. So as I told you, Lucas has been analyzed for heavy metals, and among them we have seen the copper is one of the important heavy metals that has been analyzed. It's correlated with soil properties like pH, texture, organic carbon, of course with other attributes like climate, geology, and management. But very important, we have seen also anthropogenic sources for copper contamination, like the fungicidal treatments, specifically for vineyards, the liquid manure, the sewage sludge, of course the atmospheric deposition, the mining activities, and some local industries, and of course the impact that particles coming from car brakes have in copper in soils. Vineyards unfortunately has the highest copper concentration in EU, and mainly due to very frequent fungicidal treatments, olive groves and orchards, and this was published by Balabi this month. Recently also we published the mercury distribution in EU, and this again takes place with the Lucas because mercury was analyzed there. It's not mercury, doesn't seem to be, even you see that the map, the mercury is not a serious issue in EU, but mercury somehow relevant to natural properties is linked to soil organic carbon, temperature, to the NDVI and land cover. But very important driver, we see all the outliers close to old mine production of mercury, like the Monte Meata in Tuscany, in Spain, some hotspot in Slovenia, in Slovakia, and some coal power plants. So we have seen with various analysis, we have seen where the outliers are, and then we investigate why we have those outliers. as I told you, we don't stay just in silos, but we try to link the various modeling results. So here you see the previous map of Mercury combined soil erosion with the sediment fluxes. So we try to combine those two modeling activities, and we try to see how much mercury is released in the seas, and we investigate that the Mediterranean Sea received most of the mercury, almost half of the mercury, because it's a toxic element that has a health issues. This is due to high mercury content in Spain, in some areas in Italy, in Slovenia. And there you have hotspots of soil erosion. So unfortunately, you have this combination which may provoke quite high release of mercury in specific seas. At global scale, I will give some information what we're doing. For us, it's very challenged that the work done at very local scale or farm level. Then we try to upscale this work at national level. Then we produce our results at the EU level, which is our main area of interest. But of course, we do some work at global scale as well, because we have this expertise, and sometimes we can be contacted by FAO or other organizations, and we produce these data sets also at global scale. So I'll give you some examples. Similar to the EU, we collected high temporary rainfall data. High temporal means 30 minutes intensity data at the global scale. This took place for 63 countries. More than 50 scientists have been involved, 100 organizations, and we collected this kind of data for almost 3,625 stations. We speak about 60,000 of years of high temporal data. And based on those data, we produced the first global rainfall erosivity map, which has to do with as an important factor for soil erosion, of course, but also for other aspects, climate change as well, because we can see where the rainfall intensity is higher, and of course in the tropical you see that this is much higher than in other areas, like in temperate or arid areas. And this was an important input to produce the global soil erosion map. This was produced by Borrell in 2017. We see that soil erosion at the global scale is much higher than EU, and almost 36 billion tons of soil are eroded per year. Another driver besides the rainfall intensity is the land use change, and we see that in croplands the soil erosion is quite high. I mean, half of the soil erosion is taking. I mean, 11% of globe are croplands and are responsible for 50% of the soil erosion. So this study is not just a map; it's much more, because we see the Earth system dynamics. We see with this study which are the main Earth system dynamics, which are the main changes, land use changes that provoke this erosion change, because we didn't monitor just erosion for 2020, but we monitor also the change. You see on the map on the bottom right, the change between 2000 and 2012, and we see that there is an increase of soil erosion, unfortunately, due to conversion of much forest land to cropland. Again, here we try to combine our global erosion stuff with an existing phosphorus estimate map to see how much phosphorus is lost. Why phosphorus? Because phosphorus is an essential for plant growth. It's a key limited for nutrient rich food. It's a threat for ecosystem health. And of course, it's lost with soil erosion and may provoke a lot of issues in the seas. And as you know, phosphorus is limited, because you have certain mines, and there is a lot of geopolitical interest on this topic. Therefore, we want to combine those data sets to estimate how much phosphorus is lost and from where. And we see here the main phosphorus losses, which from different agricultural systems. So the range is between 1 and 12 kilos per hectare per year. Very high losses in Eastern China, Indonesia, where you have a lot of erosion, but also a lot of phosphorus inputs, and some high loss as well in India regions. This was recently published as well by Allewell et al. Just coming out of the press, we do also some soil erosion projections, meaning that our erosivity data set that I showed you, the 3,625 stations, are projected towards the future. I mean, what will be the erosivity projections in the future? Because we take into account the climatic models. We input in our model the climatic models and try to do this projection of erosivity. and these are important to show that erosion will increase at global scale between 30 and 66%. This range you have because you have a lot of models and a lot of RCP scenarios that have RCP 2.6, 4.5, and 8.5. Similar study has been done recently in EU. The first one at global scale has been published by Borrelli and Nas. The recent one has been published by me recently, and we show that in EU the change will be much less, but of course the erosion is not such a big issue in EU like at the global scale. So I'm going towards the end and give you some notions, some examples. You see that I present a lot of maps, a lot of data sets. We have followed different modeling approach for spatial interpolation. Spatial interpolation for us is critical. I mean, you have a lot of points, many times in Lucas or other datasets like the rainfall erosivity, you have the stations with the erosivity device we have to interpolate. So we have followed the Gaussian process regression for global erosivity and the European rainfall erosivity, the cube-based approach for soil erodibility in EU, the multivariate adaptive regression splice maps for the physical properties that I presented. I mean, the clay, silt, and sand, the Gaussian process regression for the chemical properties, for the nitrogen, phosphorus, the generalized linear models for the copper distribution, the random forest for the mercury. Of course, why you have this variability? You have this variability because of the performance of the model, because of the inputs that we have, because of the covariance that we have. So we test various approaches. We are very open in following one or another approach. Some concluding remarks about, I will have two concluding remarks, one about modeling and one about policy. Regarding the future, we see that we go towards object-oriented solutions. So from pixel or from from a different, from a shape file, we go now to see what's cultivating the land. It's very important for us, the farmer, what is doing. So we follow more, this land parcel approach will be very important for us. The Lucas 2018 Earth observation have a lot of potential if combined with Copernicus, another that's on crop calendar. Important for us is to run some policy scenarios, some scenario analysis on climate, on land use change. I mean, the main scenario analysis are either climate or the land use change or the policies. We are close to policy interface. We know what the main policies are predicting. As I underlined many times, we focus also in model integration. I mean, we have different soil processes and try to integrate them, like carbon loss, biodiversity loss, erosion, diffuse pollution, phosphorus, and incorporate them in earth science modeling. And more to come. A lot of things will come now. As you have seen a lot of stuff in soil organic carbon, in diffuse pollution, you will see more and more carbon on soil biodiversity and DNA analysis, because around 1,000 points of Lucas have been analyzed for DNA, and they give quite interesting results, which are relevant also for policy, but are really exciting for science. Some concluding remarks regarding policy. The common agricultural policy will have a strong environmental component, which allows us now to have some impact in the provisions or in predictions of how various processes on soil will go in the future. So we have to do a lot of work there. How we can protect our soils with which better management practices. The agricultural management practices are important for soil conservation. EU is a front runner in sustainable development goals, and we produce a lot of stuff there. The EU Green is the main motor now, with main strategies like the biodiversity strategy to halve biodiversity loss, the climate law in order to reduce greenhouse gas emissions, the farm to fork in order to reduce nutrient losses, and of course the zero pollution in order to reduce hazardous material and pesticides. We expect now the new soil thematic strategy that will come very soon and will give quite a lot of work on how we can achieve land degradation neutrality by 2030. And but unfortunately, a binding legal framework of soils is missing, and this is quite important for our work. As I told you, we established now the European Soil Observatory, which has a lot of work and has different objectives from research, policy, data, etc. And one important event that takes place, and you are welcome to participate because it's an open event and everybody can register, is the European Soil Observatory Stakeholders Forum. So there will be one half day, I think, high policy relevant, high level policy speaker, but the rest of the days will be, we try to involve all stakeholders, I mean policy makers, researchers, regional authorities, farmers, NGOs, citizens, everybody is welcome to be there. We have 6 sessions facing the major challenges in soils like soil biodiversity, soil pollution, soil erosion, data, etc. And we had a nice idea that during this 3-day soil forum, we have a young researcher forum. So we'll dedicate one half day in young researchers. So if you are a PhD student or you have taken a PhD no longer 3 years ago, please submit an abstract, because we dedicate half day in young researchers, and we want to listen to you, to the young researchers, how they see the research on soils or in different environmental aspects. So these are my contact points. So all the data that I presented are available in ESDAC. You can contact me on any issues. So thank you, Tom, for giving me this excellent opportunity.
Thank you, Panos. It's amazing how much work you do, you and your group. It's difficult to follow.
Yes, I know.
Yeah, so, but it was really good overview, and we have some time for questions. I was just looking at the chat. If there's any questions, please post them through chat. And I'm also looking here at the room, the conference, if there's any hands in the air. Yes, there's one question. We will bring the person for the sake of the hearing everything. We bring the person next to the microphone. So here's a question by Lena Halunova, professor from CTU Prague.
No, I cannot hear you, unfortunately, no.
No, nothing?
No, no, a little bit
Microphone
louder.
is on. Wait.
Yeah,
no,
a little bit louder, I see. Okay, please. No, very. I see very clear. I listen very clear, Tom, but not you.
You heard me, but you didn't.
Yes.
Interesting. Can I see? Tell me the question. I will repeat. Okay. Yes. Is that the question? Is it just about that? Okay. There are two questions. Can you hear me, Panos?
Yes. Very clear.
Yeah. One question is how you're related with IUSS. So how do you work with them? And then the second question is for the soil erosion. What is the best resolution you have at the moment for EU?
Okay. If I go for soil erosion, it's 100 meters that we provide. Of course, as I told you, this is at pixel level, but we prefer to have it at farm level. So our next objective is to go in farm level. The main reason for having the 100 meters is because it's driven by land use changes, and there we have the CORIN plus other data sets that drive us at 100 meters. Now, regarding the USS, as I recall, is the International Union of Soil Science, if I'm not wrong. So we have some exchange of mail. I will try to involve in the European Soil Observatory, so they will come. The president of the USS, Constantini, will come and will present there. We have some informative, we exchange mails. They take some of our information in their newsletters, but it's a different type of organization. We are researchers that we provide policy support, but they're quite an association that keeps all the soil sciences society under the umbrella. That's all.
Okay, thank you. And one more question for me. What are the biggest constraints for estimating like soil degradation, land degradation over Europe? What are the biggest constraints? We have lots of talks in this workshop, which about land cover modeling, biomass emissions and things, but soils are hidden. It's a really different thing.
Soils is hidden, Tom. It's hidden because yes. I'll give you an example. The reply is very easy. It's the privacy issue. It's the privacy issue which gives us a lot of problems. We have this privacy issue, and I think with Lucas we're just in the gray zone, because if you go in the field and you sample of a farmer field, as soon as you analyze the physical and chemical properties, if you analyze pH or maybe soil organic carbon or clay and silt, is okay. But since you start giving information about heavy metals, about pesticides, then you have an issue. But on the other side, we should see that soil is a transversal issue. It's not just a private. If you have one field with X or Y properties or X, Y problems, this should somehow be acknowledged, because in this field you produce food, and this is important. So the privacy issue for us is an important issue, that the privacy which does not allow to have a lot of inputs. Another issue is that we should have a better collaboration on integrating all these monitoring activities. I mean, we have the 20,000 soil samples of Lucas, but why not to have 250,000 soil samples? Because we know that France has another 50,000 samples, or Germany has another. So it's very important that we integrate all these efforts in one effort, and we go with much higher number of points.
Okay, thank you, Panos. For the sake of time, we have to stop.
Thank you.
Stay with us. There's a lot of interesting talks. There's also a session on the virtual reality and augmented reality just before lunch break. So there will be also for you that are the week. There's a table you see in the middle. Our colleagues from CTU will give a demo of the virtual reality, augmented reality. So please, they brought the equipment here. Thank you, Panos. We continue with the next speaker, who is Chris van Diemen. Let me turn this off. Chris van Diemen is our staff at OpenGeoHub. He's a young researcher, and he's been working especially on the analyzing Landsat data for visualizing land use change, and we have a lot of results. So please, Chris, the floor is yours.
Okay. Yep.
Next slide. Thanks, Tom. All right. Yeah. Hi, I'm Chris. I'm with OpenGeoHub. I'm a research assistant, and proud to be here to present some of the work that I've been working on for the last couple of months. Yeah, so I want to talk about visualizing 2 decades of land use change. So we have worked very hard last years, or I'm only with OpenGeoHub for 6 months, but I get the nice job of actually showing all the results, showing off all the results. So that's pretty cool. But most of the work is actually done by Leandro and Martijn, who you heard speak today already. So here I want to point out the EU map, where we also publish most of the code that was used to produce these things that I'm showing you, and the preprint where some of the visuals that I show will be, they are in this preprint of the work that Martijn has been doing. So I want to talk about, I want to talk about 3 main things. So the NDVI slopes, because I think it is a metric that most people understand, that is used for quite a while. So it's kind of a part of the input of our models, but it shows us also information about, it's understandable, and yeah, it's a nice metric to look at. And then the probability slopes, because I really think that's something that hasn't been done so much before, and that is really now possible with using the ensemble machine learning approaches. And then class changes that are another result of our approach, and kind of show what it means, what was modeled, so the land use that was modeled over these decades. So this is a quick overview, just to remind you. So we have the temporal Landsat, then we can apply a gap filler, so we get nice clean data. And that is also, part of this is the NDVI data. So that is what it will now be showing, that also goes in to the space-time overlay, and also is a variable in the machine learning that we apply. So it's kind of an input, a variable for this model. First, to get a bit of an understanding of what can we see in these in this NDVI values is a little farm that's not so far from here. It takes you 30 minutes to bike there. I would definitely recommend you to do that if you have some time. It's a farm that transitioned to organic agriculture in 2009. And if we look at the Landsat values for this field in particular, we know it was transitioned from crops to organic cattle, and we use a decomposition of the seasonality. So this was what Leandro also talked about. That's the same approach that we use here, and also shows the strength of the EU package, where we can easily implement approaches from other packages on a large amount of data. So here we see in red the average values for the NDVI for this field, and in blue kind of an average mean. And below we see if we decompose the seasonal and the trend. So the red is just the trend, and the yellow is just the seasonal effect. And if we decompose it, you can quite clearly see this where we change from a crop type to a cattle kind of just grass, much more stable type of agriculture. So that also shows us very clear indication of what's happening here. And then we went a little further and just mapped this trend for every pixel in Europe at a 30-meter scale. And so here, and at the top we see the same graph that I just showed you, just for 1 pixel in Sweden for a forest that is regrowing. Let's see, there is a little map here. So it's over here. It's a little forest that just has been cut, and then it's regrowing. So we see kind of a increasing trend if we decompose this signal into just the trend, and we fit a ordinary least squares regression on these values. So we get a slope value that's positive. And if we do that for multiple pixels, we get this kind of image where green is a positive slope and red is a negative slope. And then here I want to show you the probability values for coniferous forest. So actually here you see, if we apply the model for this pixel for every year that we've gap filled data, then we see that the model, the probability value for this pixel to be a forest is increasing. And also this we can map spatially. So I think that's quite interesting. And then I want to focus a little bit on this one to show you, well, let me skip this for sake of time. So that's really just the decomposed values mapped for every pixel in Europe at the 30-meter scale. That's then I want to go further to these slope values of the probabilities, and show you that this impacts how here we can have some deeper understanding of how the landscape is changing, because we can see this for every class that we have that we use. So 43 or something like that. So that gives us more information about what is happening in Europe. And then for me, it's a bit the challenge to see how we can visualize that. So here's another example where you can check if you want to have an understanding, like really, what does this make sense in reality? You really see that if we have, for instance, here a positive slope for, in this case, barely vegetated area, then here we see that in 2009 there was a forest, and then in 2017 that forest has disappeared. So it makes sense that we have a positive slope for the probability of being a barely vegetated area. So that's just another example. And then an example for a reforested site. So if we look at the situation in 2006 and in 2019, we see that the probability, the slope for the probability values for coniferous forest is actually positive. So that makes sense. So then going to the land use classes. So in a model, the class with the highest probability is chosen as the class, and then this is, if you visualize this for 20 years. So here we see Rotterdam, where they build a new part of the port, where you get, well, yeah, the most clearly visible change from water to land, I think. But how can we visualize this on a European-wide scale? That's another challenge. So we have many different changes, of course. So this is just kind of a simplified way we can show all the changes that we have. And this is also in the reference data that I provided. And then we can get something like this if you apply it for larger areas. So we can see that there is, yeah, some red there. So there is, of course, disappearing. But as we have seen also here, some pixels, they kind of fluctuate. This is also something Martijn mentioned. So we try to apply a bit of a filter so that pixels that have changed to a class between being one other class in another year, we filter them out. So we get a little bit cleaner results. So here we see if the class has been this value and then just jumps one time, we just pull it back to be that class. So this is also done for all the data that we provide in the portal. And then one way we imagined we could visualize this is to look at the aggregated over 5 kilometer blocks. So just to check what is the main change within every 5 kilometer area. And then we get maybe yeah, surprising image of Europe, where green would be reforestation and brown would be deforestation. And then we get, of course, in a very interesting discussion with the people from Sweden. But that's what we see in this image. So you might ask, can you enhance that a little bit? So yes, we also, that was 20 kilometer blocks actually. So we also look at 5 kilometer blocks. So it becomes already a little bit more detailed. Of course, we have 30 meter pixels, so we can go much more detailed, but this aggregates the results a bit and shows you more of where the changes are happening. But of course, if you just check the prevalent change, then even if there's 3 pixels changing, then it could be one of these pixels on the left here will become green. So it's important to look how many of the pixels in that area has actually changed. So how much of this area has actually changed. So we generate these change intensity maps to really see where the changes that we mapped are actually happening at a larger rate. And I think if we combine this, it becomes really more obvious where areas are stable and where areas are changing in whichever way that we have that come out of this model. So I think that's a very interesting result and really allows you for any change case or any change to really see, okay, what classes are. So to go from a very broad view to zoom in to what's actually happening here. So here we see, for instance, there's a lot of deforestation apparently here, and maybe reforestation in this area. So if for your particular research, maybe it would be interesting to look before you kind of start to look at these maps and see what you can expect in this area. So I think that could be very useful to people. And then we can combine these 3 things. So we have the NDVI slopes, the probability slopes, and the actual land cover change to really get more detailed information about the area we're looking at. So for instance, if you look at some area here in Sweden, we see that, yeah, some areas are probably being used for forest harvesting, and some areas are regrowing forests. So it's not so so clear cut that it's just deforestation, and the same in this area in France. And then some things we really cannot explain yet using our approach. So I think that's also interesting. So in the Alps, for instance, we see negative NDVI slopes, but we don't really see very clear signal in the probability slope. So that's really something we are looking into now. But we do see that these areas are, yeah, they kind of turning into deserts according to the change maps. So that's something for me, it's very interesting to look at these maps to see what is clear patterns and what can it tell me about the changes that are happening. I think that's all I got. So if there are any questions, please shoot.
It's super interesting. But with the ADVI slope map, it's available on in the maps of the you can look at it. Yes, question.
Thank you for the presentation. So I have a question that I studied development for development. So my question, what's the value you show in graphs mean for the year of 2008? There is one value. So what is the average value of the area of one pixel, or you have areas which are homogeneous? And with an average for a couple of weeks or how close?
Which one? Is any all data? Yeah. So the maps, the most maps that so the question is, what do the values actually mean?
Right.
Yes. So for all the maps that I'm showing, the most of the maps that I showed, it's either NDVI slopes or NDVI.
But so which area of one pixel?
Yes. So we use the Landsat data. We apply a gap filling approach, and we harmonize all these data so that there is no clouds or anything in it. And then the values that come out is, yeah, that is kind of a clean data set that in the workflow we visualize that like this. And then on that data, I apply, I decompose the seasonal effect.
Yeah.
And then from that decomposed signal, I just take the trend. And on that, I fit a regression.
Yeah.
And that slope, that is what I'm visualizing. So yeah, it's a lot of steps.
I understand for 100 areas, for every pixel, for many graphs like that.
Yes, we did this for every pixel. That's correct. This is just an example of one pixel. So there's one single pixel here where X marks it. And then this one pixel, this is kind of the signal for this pixel. So all the red dots, they are the NDVI values. And then we decompose it using the stats model toolbox. And then we get this is just the slope, the trend. And then on that, we fit a regression of which we just visualize the slope here. So that's kind of a trend. So also what Leandro discussed, we chose this approach because it's relatively compute not so intensive. And so of course, there's other approaches to do this, the be fast as mentioned. But I think it's a nice method to kind of show a direction of change.
It's very difficult for it because we have the videos for it. The development during this area of nature is different than of the conifers, and it depends also on the height of the sea level and so on. So there are multiple conditions that have to take into account, and also the land expectancy of trees is different. So the good trees, even though they could look like a forest, well, I will do, but I will just specify they will be forest, because there are 3 years, so we have 4 plants, and the specification looks like it is good, and also there's no everything else. So it's very complex, so that's why I think it will be really important.
Yeah. So the point you're making, I'm just repeating it for the people online. So the point you're making is that it's just really complex. So the graphs we're showing might be a bit too simple to look at, too simplified to visualize this complexity. Yeah, I think that's a very good point. Thanks for making a point. And I think I hope people like you or people here that they can take this data and they can actually say, okay, I apply my own analysis on it, and I can show you that it's either wrong or it's actually useful, or we try to put this data out in the open so people can use it and discuss this and yeah.
Non-linearly related, but it's non-linearly related with different land use and land cover. But still, the way we compute it, it's all documented and it's based on harmonized data. We don't introduce any bias. Thank you. We have to stop.
Yes.
Sorry.
No worries.
So we continue with the next speaker, who is also a project partner from Zagreb, Croatia. We'll make him a co-host. Just a second. Josip Križan from Multi-One Zagreb, Croatia. He's going to talk about the data set they made in the project, which is really cloud removed and cleaned, complete, consistent Sentinel product for Europe. Very exciting, super exciting. It's also part of the project. We're very happy to have Josip with us. So Josip, please try to keep it to 20 minutes and leave some time for questions. The floor is yours.
Hello. I hope you hear me. Well, I'm Josip Križan. I come from a Multi-One company. So we made this pan-European seasonal cloudless mosaic with Sentinel-2 images. Can you see my screen? Okay. So there is a lot of publicly available remotely sensed data, and it has been rapidly increasing in recent decades. But the data are not generally freely available as harmonized and analysis-ready products. It's so process of mosaicing these images to produce something that's homogeneous and cloudless can become a little bit cumbersome at larger scales. So this is the description of data set. So a source of data were Sentinel-2 level 2A open data on AWS. We took the 6 bands from there: blue, green, red, near infrared, sphere 1, sphere 2. We took for every band, we took 3 statistics: 25, 50, 75 percentile, and count of valid values, so per pixel. We produced 4 seasons per year in 2018 and 19, and winter and spring for 2020. So these are dates when these dates are aligned with GLAD IRD products. So that it was idea that we made the fusion of this dataset with that Lancet product. That's it. And all data is resampled to 30 meters resolution in this projection 3035. Okay. So data can be accessed in the Zenodo platform. There is you can download it from here, or that's okay. Or there is also made cloud optimized geotiffs on Wasabi, so it can be accessed directly via web. It can be accessed directly via through QuantumGIS. This is the pattern of links. And for band, there is red, green, blue, near sphere 1, sphere 2. And for seasons, you have to replace this start date and end date in the links. If you want to access this with GDAL tools, then you have to add prefix VZI curl example. So this is example. How can you access this data? And yes, these data are these data are scaled to bytes. Originally, data is in 16 bits, but just for matter of space of size is really big, so we have to scale it to bytes. So this is how it looks. I can show you. I will show you in QuantumGIS. For example, this is summer 219, and this is autumn 219. It's not perfect, especially this northern part, but so how it's done. First we calculate the mosaic of one season, one band in one sentinel tile and relative orbit. So all the bed values that has clouds or cloud shadows is masked out, and then it's calculated 25, 50, 75 percentile and count of all valid values for every pixel location, and this intermediate result is saved back to temporary S3 location. So this is done for all. There was all 137 Sentinel-2 tiles. So this is a grid of Sentinel-2 tiles. So first, it was every tile is calculated independently, and then all tiles that are in the same season, band, and orbit is stitched together. It's just taking mean value of overlapping, not tiles, overlapping pixels. So this looks like something like this. So we have these tiles, but we have these orbits. So everything that is in one orbit is consistent, because satellite is all these images are taken one after another, so there is no visible difference between them. But when we put neighboring orbit one by another, so then we have see this, that we have they are not aligned perfectly. So this was these two orbits are then stitched together by using inverse distance weight mean with respect to the distances from every pixel to this central orbit line. So that way, when we put these all orbits together, we have this final product where there is no stripes, there is no visible transitions from one orbit to another. Yes, this is so. For example, Winter 219 RGB composite looks something like this. There is a lot of these white values because there is it's just snow. Snow wasn't masked out. And so spring and summer.
Maybe you could zoom into some area just to get an idea.
Yes, I can zoom it. Yes, too. So this is directly from Wasabi. It's really fast. So this is, oh, that's it. It's 30 meters resolution. And okay, this is RGB composite. I made this near sphere composite too. It looks interesting. This is this is from near sphere 1 and sphere 2 bands. Okay. So yes, that was algorithm that we used, and this was computed on multiple spot instances on the AWS. Every instance have 64 to 72 vCPUs and 500 to 700 gigabytes of RAM. And so this so every season band tile orbit mosaic was one independent job, and it could be calculated in parallel. So the system is made of two components. There is client script that runs on these multiple instances, and it fetches job descriptions from one central server. And that server, there is API, and behind this API is a Postgres database that keeps track of all jobs done and all jobs that need to be done, and take care that there is no duplicate jobs and so on. So this approach is scalable to any number of instances with CPUs. So of course, up to total number of jobs. It's not well, it's not really correct. This scalable. If you have too many instances, then this central server becomes squashed. It's too many, but okay, that can be. So there is 137 S2 tiles, and it was around 42 to 43,000 images, Sentinel-2 images for each of the band. So for each season, to make this whole mosaics, it was really a lot of data. Well, that's it. No, I was really quick. Okay, any questions?
Okay, thank you. And so this data, can you go back to Zenodo, just show us one more time at the moment? So it's available in Zenodo, and it will be put also in the Open Data Viewer. And also at the moment it's available through Wasabi, so you don't have to download everything. But it will, basically the data is ready. What about the gap filling?
Well, we didn't make any gap filling. We have this count layers where there is, for every pixel there is a count of numbers. So if it's low number, then this pixel is not really reliable. So it can be used like gap filling, but we didn't make any gap filling at the moment for this.
Okay, but it's a fantastic piece of work, and we have both Landsat and Sentinel. We have inside the project prepared analysis ready. Okay, with your data, the gaps with the Landsat, we fill in all the gaps. What is your impression of the difference between Landsat and Sentinel? Because there's it's the same resolution, it's the kind of multispectral, same type of bands. What is your impression so far about the differences, Landsat and Sentinel?
Well, I don't know. Landsat has 16 days with revisiting time. Sentinel has five days. So it's almost 3 times more data on the timeline. So that's a big deal. So there is there is less gaps for that. But then Landsat has this Landsat 7, Landsat 5, Landsat 8. So that's you have more than 20 years of Landsat, while Sentinel is only from 2016, 17, so on.
Okay, looking for questions from audience, if there are any questions. So there's again, this workshop, we are having a couple of launches, and one of the launches also we have made Sentinel cloud-free analysis ready data set for people covering all of Europe at 30 meter, basically all bands, and you have a 3 quantile. So sometimes for some analysis it will be the lower quantile, for the other analysis it will be higher quantile. But this is really fantastic, and thank you, Josip, so much for connecting, and thank you for your work. Yes, we look forward to seeing this data also in the data viewer, and we look forward to in future filling the gaps and then having every pixel, like with the case of Landsat, every pixel with a value. Thank you, Josip. You can stop screen sharing now, but don't go away. We have one more presenter. I will just make Karel just a second. So we have Karel Pavelka with us. He's connecting from Prague, and he's also in the GeoHarmonizer project. He was in charge of, making demo versions of the augmented virtual reality of the European data science year. So please, Karel, can you say something?
Hi everyone. It's good.
Yes, we can hear you. Can you also share your screen and turn on your video, please?
Yeah. So as every remote connection start, everybody see the presentation and the video?
Yes, we see you exactly.
Okay, super.
Video and presentation. So please don't take too much time because people are slowly getting ready for lunch. But
okay.
Give us a demo, and we have a table here. Your colleagues from Prague have set up a table, and everybody's eager to come and play some computer games with the European data. So please, the floor is yours.
Okay, so I will be quick. I know you are hungry already. So there is a little roadmap planning about this part of the GeoHarmonizer project. It's more like an experimental part, because we focus on the new technology like VR and AR, and a lot of the fields now join this technology and trying to do their best with the field of selection. And we also want to do this as a visualization technology for the GIS data, and especially now for the DEM models and land cover models. So we try to connect this new technology with this data, and this roadmap shows how we split all mine targets into the parts. We already done the 3 big steps for that, and the steps was feasibility study for each technology, because we will develop 2 separate program applications. One will be VR. It will be for computers, and you can use it as a normal exe file with I hope with every HDM VR glasses. So it will be accessible for almost all users with VR headsets. And the second application will be supported by Reality Kit AR. It's from iOS. We specially target to the iOS devices, because in the new iPads, they add the LiDAR sensor, and for AR and for anchor of the AR models, it's super improvement. So it looks really good now, and it's working really well. So this is our target, and this is why we use iOS. Okay, in progress now. We already done VR demo. You can try it with our colleagues. They already prepared a stage for it, and we plan it until the end of the year. Do both application and release it as a beta application as full. Now in VR demo, it's restricted features inside, and it's only the Netherlands inside. But we are planning to put inside also the Czech Republic. This is how feasibility study work. We determine our data sets. We use the DEM model, the classic model, the GeoTIFF, and trying to put it in the 3D objects, because as I said, this is a new technology, and a lot of the engines what is working with virtual reality is not supporting the GeoTIFF and a lot of the classic GIS models. So we need to find a workflow how we put the all datasets inside. So after that, we know how the data flow is working, and we prepare all of the data for these 2 applications what we will develop. We found a workflow that we will share with others. We will do a GitLab folder and put everything inside. Also, the Martin did some scripts to the QGIS for the preparation of data, and we will also share this also, that we will do a really simple tutorial how with the open source data people can do the visualization of this same kind of data like we use. So this is a classic part that we split to the tiles all over the country. Here is the Czech Republic, and we split it into 118 tiles. After that, we generate a DEM model for every tile. We use the 3JS plugin into the QGIS that he converted the DEM geotiff to the 3GeoGebs. It's a GLTF. After that, we generate for every tile the PNG tiles for length cover, and we cover the 20-year of length cover sets on it. And finally, we use the OpenStreetMap for every tile, and it's working like the basic alpha texture. So in the application, it's working like in the normal map viewer, that if you start to viewing the length and select the length cover, so you can use the map opacity and blend it with the length cover. So you know where you are and where the data is situated. And now it will be really quick because I hope everybody will try it who is in Ireland. And this is how the place look like. Just only the small navigation that you know where everything is. In the front here, you have the tile selection. It's working like the main menu where you select the tile. In the right side, there will be an overview if you select the right tile and if you really want to use it. And after you know that this is a tile what you want, it will appear in 2 stages, here and here. I will skip a little bit for it. This is the main menu, how it look like. It's you have the laser pointer in your hand and you will select the tiles. After that, it will appear, as I said, and there is 2 stages. One, as I said, as an overview, when you can walk around. It's a small model, but you can step on it and just watch it, and you can view the elevation of the model because one is a beveled, so the shadow is doing the great job here. And the second stage is the comparison of the tiles. So you can choose one data set in the left side and one data set on the right side, and you can comparison them. And there is one more stage. It's now in the demo, so we have only one tile here, and we also have the animation that all 20 years will start after 5 seconds, I think it's said. And the animation will start, and it will be like a loop. So every 20 years will go 5 seconds after 5 seconds. This is the beveled model that you can recognize the height of the model. This is how looks like the AR application, the second application. We already developed some demo, but it's too hard to implement it now because it's more complexity than VR application. So this application you will see in the next year in Prague in conference, and it will be ready for you whole Czech Republic in the AR dataset. This is only for imagination how it will look like. This is our expected outputs. I already said that it will be the 2 separate application, AR, VR, and it will contain Czech Republic and Netherlands. Our application will support the new devices with LiDAR sensor because we think that the LiDAR sensor will add a lot of the companies inside of the phones, inside to the tablets, and I think everybody will use it for AR. because it's really improved the technology. And what is important that we will do the final report and the tutorial and folder with all of the scripts that every user, because we use only the open source software, and every user can download the data what they want, and if they follow our tutorial and use our scripts, they can do this visualization that what they want. So this is in a short all from me. I hope everybody will try it and look on it, because as I said, this is the new technology, and a lot of the fields are connecting with this technology now. And I think it will be a future of the visualization of data from all of the world and a lot of the fields. So,
thank you, Karl. Thank you, Karl.
Yeah.
That's a great introduction. It's difficult to like visualize, you know, effect of or impression of virtual reality, augmented reality, and that's one of the reasons why we brought this equipment here. We have it at the week. Unfortunately, people that are online, they will not be able to get that impression. But it's a nice teaser for the next workshop next June in Prague. So if you come next June to Prague, then there will be also augmented reality and virtual reality. So you'll be able to explore this European Environmental Data Cube, not just by using a web browser, but also just, you know, just in a space and seeing it in 3D and 3D plus time and scrolling through maps with your hands, basically. So we're really looking forward to that. Thank you so much. So what is the plan now, Eva? How do you suggest people testing? How many people can test at the same time? One person, okay. So we have a lunch break. Thank you, Karel. We can disconnect. And thank you all for following. If there's any questions, please put in the chat. Otherwise, we will now disconnect, and please come back. Please come back for after the break. We continue at 2 o'clock with a keynote speaker, Freya Vamborg. So also very exciting keynote about the state of the European climate.